Hello, good morning, all. Elizabeth Miss, are we audible? Yes, sir. Okay. So let's wait for 5 more minutes, right? Let everyone else join. Okay. Good morning, all. We are about to begin today's session. So we request you to be ready for the session.
Ma'am, should I start now or are we waiting?
No, ma'am. We are starting right now.
Okay, so I can start now.
Okay.
Okay. So good morning all and welcome you all to the second day of machine learning.
1 minute, ma'am. 1 minute. 1 minute. Sorry.
That's what I was asking. Okay, ma'am.
Okay. Sorry.
No, I thought we were waiting for participants to join.
No, already 22 participants have joined, ma'am.
Okay, fine. Yeah, that's fine. I'll.
Okay, pardon me, ma'am. Okay, good morning, everyone. A warm welcome to day 2 of our faculty development program on machine learning from fundamentals to deployment. Yesterday, being the day 1 of FDP, we had an insightful session by Dr. Jisha Mariam John on the fundamentals of machine learning. The session provided a clear introduction to key ML concepts and offered a comprehensive overview of various classification algorithms, helping us understand their principles and practical applications. Building on the strong foundations laid yesterday, we are excited to continue the journey today as well. With that, I warmly welcome you all to the second day of our FDP. Due to some unforeseen personal circumstances, our originally scheduled delegate, Dr. Suchitra MS, Assistant Professor, IIIT Kottayam, is unable to join today. We appreciate your understanding and are pleased to inform you that the session will be led by an equally accomplished resource person, Dr. Srija MU, Assistant Professor, IIIT Kottayam. We are grateful to Dr. Srija for graciously accepting our invitation at short notice and for being with us today. Thank you, ma'am. I'm confident that this session will be insightful, engaging, and beneficial for all the participants. Please join me in inviting a warm welcome to Dr. Srija MU to today's session.
Dr. Srija is currently serving as Assistant Professor at Indian Institute of Information Technology, Kottayam, and a researcher specializing in explainable AI, computer vision, video analytics, machine learning, and deep learning. She earned her PhD from Cochin University of Science and Technology and was a recipient of the prestigious Chief Minister's Navakerala Postdoctoral Fellowship. She has published extensively in reputed SEI indexed journals and conferences, secured multiple funded research projects, and holds patents in areas such as intelligent surveillance, healthcare AI, and energy management systems. Her research focuses on developing AI-driven solutions for healthcare, smart surveillance, transportation, and animal welfare applications. Let us warmly welcome Dr. Srija to begin today's session. Over to you, ma'am.
Thank you, ma'am. You may begin the session.
Okay. So thank you for the warm welcome and welcome all of you to the second day of machine learning from fundamentals to deployment. As ma'am has rightly said, this invitation came as a short notice. So if at all there is any continuity issues in what I try to cover, please pardon me and you can...
No issues, ma'am.
Okay, you can give any suggestions at any point of time, that's fine.
Yeah, sure, ma'am. Sure.
From what I know, yesterday's session covered the introduction into machine learning, and
Yes.
I think you were given with a overview of what different kinds of learnings and different tasks like regression, classification. All
Yes.
these were covered as what ma'am has told me because we had a communication yesterday. So I think she has stopped with linear regression, logistic regression.
Yes, ma'am.
Yeah.
Yes, she has
So she
covered
has
all this.
informed me that decision trees were pending. So she had asked me to kindly start with decision tree. So I might
Decision
start
trees.
with decision tree. Although the topic assigned was unsupervised learning, we'll just cover decision tree because that is also a very important topic in
Okay.
supervised learning. So I'll just begin with that. I'll just share my PPT
Screen, okay. Okay, ma'am. Thank you.
Yeah. Can someone just confirm whether the screen is visible?
Yes, ma'am, it's visible.
Okay. And I'm audible too, right?
Yes, yes, that's right.
Thank you. Thank you.
Okay.
Okay. So, as the session begins, I'll just quickly recap through the intro part. Can someone just tell me what did you understand by the difference between machine learning and traditional programming? I can see Danya. I mean, I don't know who that is. I'm not familiar with you, ma'am, but somebody is smiling there.
Yes, ma'am. Yesterday we started with introduction to ML.
No, I was just quickly
Then-
simply asking, what did you understand as the difference between machine learning and traditional programming? In your point of view, it's fine.
We are making machines in order to understand like we do by using various methods, and we got introduction to different classification algorithms and all.
Okay. That's fine. Yeah.
Then it is if we know all these methods, if we have a clear idea about all these concepts, it is easy to train the system and do the things in a more efficient way than we do.
Okay. So what I intended was just to have an idea of what is the difference between traditional probably ma'am has covered it. I'm just quickly recapping it. So in traditional programming, we'll be feeding the system with the data and rules, or the relationship between data is also given to the system, and you'll be getting the output. Right? For example, if you happen to know that there is a relationship between y and x as y equal to 2 in x, that will be fed as the program, and when you give a new x, you'll be getting the output as y. But in the case with machine learning, you have a historical set of data points wherein the input and output is fed to the system. System itself is trying to learn what is the relationship between the input data that you give, that is x and y. So data and output is fed, and you are ultimately getting the rules as the output. And you might have come across the linear regression algorithm, where you start with a random line and then you try to fit in the best fit line based on the different data points that you have. I hope that is covered, right? Then the different types of problems, regression and classification also, I hope you have a basic understanding of that, right? So can someone just tell me if you are planning to create a match outcome prediction model, wherein you have a data set, a historical data set, where you have the outcome as whether the match is won or lost. Whether you have the country has lost the game. So if that is the case that you're trying to predict or trying to model a machine learning algorithm onto, what kind of a problem that will be? Will that be a regression or classification problem? Win or lose? That case, classification. Okay. And the wind speed prediction, if you're trying to, you have a historical set of data where the different features that contribute to wind speed on computing wind speed. The actual speed itself, it's not just high, low, or mid, it's just the actual speed values. And based on atmospheric pressure, humidity, temperature, all these factors are already there, and you have a historical set of data. What kind of problem that will be? You're trying to predict the actual wind speed of a particular day based on the previous set of data. So what kind it will be? Regression. Okay, you can see that in chat. So I'm just moving ahead. And the type of ML algorithms also, I'm sure ma'am might have just mentioned it: supervised, unsupervised, semi-supervised, and reinforcement, of which supervised and unsupervised might be the ones that we'll be going in detail. What is the difference between supervised and unsupervised? If anyone wants to just mention.
In supervised, we'll be providing data along with the label, and in unsupervised, that labeling wouldn't be there.
Yeah, you won't have label data in unsupervised. In supervised, you will be getting label data based on which you can map the input X values onto that labeled value. Fine. So now moving on to, I'm not discussing detail into supervised algorithm. As you can see from the screen, you have example instances x1, x1 to xn, where n is a data set size, and each row will have different set of features that will be mapped into a particular label. So the example that you can see down is for each row there, with the length, width, and height, you're mapping it into a label, whether it is banana, orange, or whatever fruit you're trying to classify it into. So it is a classification problem, and it is supervised because you have the labels there. That is the case with super. I'm not going deeper here. So the popular supervised learning algorithms are k nearest neighbor, decision trees. We start with obviously linear regression, Then you can use logistic regression for the same, but generally we use that for binary classification. Then decision trees are also for classification purposes. So SVMs, these are the algorithms that we popularly use for supervised learning problems. Okay, supervised learning algorithms. So in unsupervised learning, as ma'am has mentioned, we don't have the labels marked onto the data. So based on whatever data that you have, the machine tries to learn, or the system algorithm tries to learn what are the common features that are present in the input data based on some algorithm. That algorithms will be seeing in detail over the course of the period of course. So you can see that there you can see a Donald Duck, Minnie Mouse, and different ducks, rabbits are there. Then we have mouse. So what they're trying to do is there is a beak pattern that is common to all the ducks, right? So something that is common, some features that are common, those are grouped together, and the ducks, you can see that finally after the learning process is completed, the ducks are grouped together, and the remaining mouse and rabbit, some similarities there. Actually that shouldn't happen, but some similarity is there which enforced the algorithm to group those two animals together, or those two images together. So that's what happens in unsupervised learning. Although the system doesn't know that these belongs to ducks, that label is not there, but it's trying to find out some common patterns or common features that would help to group the input data into different groups. So there are algorithms that would insist that you have to mention these many groups, it should group into these many number of groups, or there are algorithms that would find the optimal number of groups to which the input data can be grouped into. Okay, we'll learn those in the upcoming slides. So before, okay, these are just examples, we need not okay. Now just an idea into semi-supervised learning. What was semi-supervised? Was it covered yesterday?
That would consist of both labeled and unlabeled data, ma'am?
Yeah, labeled and unlabeled data will be there. And how do we, like, it's not like that. You might be having a set of samples, maybe there are different chances. As you said, combination of labeled and unlabeled data will be there. And there are also chances that entirely unlabeled data is there. So if it is a combination, you can use that set of labeled data and use it to find out groups in the unlabeled data and provide labels to the other data. There are another chance that you can use a few of unlabeled data, try to group it, provide labels, and then you can use it for labeling the other sets of data. So partially labeled data and using those labels for learning the features and trying to apply those labels into the other set of unlabeled data, that is where semi-supervised learning comes into picture. So this is actually in an application point of view, this is too important, but then we are not learning any algorithms based on semi-supervised learning. We tend to learn supervised and unsupervised. A combination of those algorithms itself is applied for semi-supervised learning. Okay, so reinforcement learning is also there, where it's a totally different approach, but those basics might be covered in the yesterday's session. We are not going into deeper aspects, but just understand that there is also another learning principle based on reinforcement learning. Now, as stopped by Jisha ma'am, I think I'll start with decision trees. Decision trees comes under supervised learning itself. Okay, and we are focusing on classification here, classification problem. And we do have different algorithms in decision trees, starting with something called ID3. So as when I checked your syllabus, I could see that ID3 is the algorithm that is mentioned for learning as part of your syllabus. So I'll be focusing on ID3 algorithm. We do have modifications after ID3 that came into picture called CART and all, but then we'll be focusing on ID3. So the full form of ID algorithm is iterative dichotomizer. So there is nothing too much to worry about a dichotomizer. At least a few might be knowing that dichotomization means that we are dividing into two completely opposite values. That is why that name comes into picture. We are just dividing the entire data into two completely opposite paradigm. So it's not like dividing the entire data set. The term itself just means like we are dividing into two groups, dichotomy, yes or no. That's the main principle. The principle behind decision tree basic algorithm ID3 is the dichotomization process, and we are doing it iteratively so that we get a hierarchy of hierarchical structure in the form of a decision tree. Okay, and there is something called entropy and information gain that we compute in each of the iteration. Any idea what entropy and information gain is? Have you heard of these terms earlier? At each iteration, what we're trying to do is, you'll be having a data set. You have different attributes there, right? Attributes are features. You call it features or attributes. What we're trying to do is, we are trying to find out the most important feature or the most informative feature that can lead to the final outcome. Okay, at each iteration. So the most important feature is first found out. That will be the root node that is able to split the other features into in a proper way, so that you can reach a decision in a clear-cut idea. That is how the tree is formulated. So before that, we need to understand what an entropy and information gain is. What does entropy mean? In any other context, if you have heard it, you can mention about it. Some sort of delay or error. Okay, disorder in a system. Fine. Yeah. Yeah, what you intended is correct. Entropy actually means the amount of uncertainty that you have in a system, right? So what we're trying to do is how a feature contributes to the entropy part. Entropy is how much uncertainty is there in the data set, which means that you cannot precisely divide or classify a particular input into yes or no, or a particular class. What is the amount of that uncertainty present in the data set that is computed as the entropy. So you have different types of different levels of entropy that is computed in the process. The process itself is a bit long, but then the concept, if you understand the concept, it will be simple. You won't have confusions. Otherwise, the step, if you're just trying to mug up the steps, it will be different. It will be difficult. Not difficult, but you feel like it's a long process. Okay. So entropy is the uncertainty. So what is the ideal case of entropy value that you expect? Entropy should be maximum, I mean, more or less. Obviously, we are trying to reduce the entropy. We want lesser entropy. Information gain, entropy should be 0 actually. In ideal scenario, or in that case, you have to have the entropy to be 0. But then that's not the case with the data sets that we get for machine learning purposes. We try to reduce it. Okay. Information gain is. So information gain is something that we compute from entropy with the aim on how this uncertainty is reduced after splitting data using a particular feature. So if you found out a feature and you're trying to compute the entropy and information gain for that, what we're trying to do is, information gain is computed based on the entropy in such a way that you're trying to reduce the amount of uncertainty, or this uncertainty that is caused by that splitting attribute is reduced after using that particular feature. So what is the information that that particular splitting node or the feature provides? That is what is found out using information gain. So it is the opposite of entropy. While entropy introduces uncertainties, information gain is something that you compute from entropy in such a way that when you use a particular attribute as a splitting node, it should reduce the entropy, or it should reduce the uncertainty that is there in the data set. And in this way, we compute this for all the attributes. And we find out the most dominant attribute. That is what is the step that we perform in decision tree. So the most dominant attribute is found out, which means that when you compute information gain for a set of attributes, suppose you have features A1, A2, A3, and you compute information gain for A1, information gain for A2, and information gain for A3 using certain set of formulas, which will be your splitting node. The most, I'm telling that it should be the most informative attribute. So how do you choose it? You have the information gain value for 3 attributes. How do you decide which attribute should be chosen as the root node or the splitting node, first splitting node? The one which is having the highest information gain, or the one which is having the lowest information gain? Okay. Obviously, the one which is having the highest information gain has to be chosen as the splitting node. Okay. Now we'll just look into the process. We'll see. We'll do it with an example. I prefer that. Like, learning the algorithm is secondary. How to solve a problem will be learning that will be easier. So that when you see the algorithm, it's pretty simple. Okay. So this is taken from a video, this example. It's a most popular example. If you go and search in internet for decision tree example, definitely you're going to see this example first. Okay. So here the peculiarity is that plate NS is the outcome variable and outlook, temperature, humidity, wind is the features. 1 second. These are the features and this is the outcome variable Y. So what is the peculiarity of this classification problem? This is a binary classification problem. I hope you all agree with me. You just have yes or no values here. It's a binary classification problem. Any other peculiarity that you see here? I'm asking based on the features, the different attributes, outlook, temperature, humidity, and wind. You can see that all are taking categorical values itself, okay? You can see that there are no continuous values or numerical values here. Every column takes up categorical values. So the one disadvantage that I would like to highlight using ID3 algorithm is that you can use only categorical values here. You cannot go for continuous values in ID3, but CART algorithm, an advancement of ID3, they have addressed it with a small slighter variation in the algorithm. I mean, that algorithm can handle continuous values as well. But in ID3 algorithm, we have to have the input attributes also taking categorical values. And the outcome variable here, the Y value, although it looks binary, it's not like that. You can have multi-class also. This particular example, although it is binary, you can go for multi-class classification also, no issues with that. Okay, need not take that into account. I just wanted to mention that. Okay. So how do we start this? As I said earlier, 1 second. Yeah. As I said earlier, what we are trying to do is we need to find out. I'll just show you the entire process first and then we'll go step by step. 1 second. I'm still there in the meet, right? I just closed the window. Okay. Okay, so what we're trying to do is, initially, as I said, we have to compute a set of entropies first. We have to compute a set of entropies first. The first entropy value that we are computing is for the entire data set. It's for the entire data set. Okay, so before computing entropy, we have the formula for entropy as, I'm sorry for the blurred representation, but I didn't get time to convert it into equation, so please pardon me. Anyway, it's a simple measure. You have the probability of a particular class. I mean, you have the probability of a particular class multiplied by the log of that probability to the base 2 and the summation of that. So we have just two classes here, right? We have just two classes here, yes or no, outcome. We are talking about the entire data set. So class represents the outcome variable. You have just two classes here. So the entropy of the entire, this S stands for sample. You can see, you can just relate it to sample. So whenever you see entropy of S, you just imagine that it's for the entire sampling data set. And you're computing the entropy for the entire set means that you're computing it for the entire outcome variable. So here you have to count how many positive outcomes are there and how many negative outcomes are there. Or if you had three classes, you will have to count how many number of each entries are there. So here only yes or no is there. So what is the probability that you're going to get a yes value? What is the probability? Total data set count is 1, 2, 3, 4. You can just count. I know it is 14, but just you can give it a count. 11, 12, 13, 14. 14 is the number of rows. So that is the total count. So how many yes is there? 3, 4, 5, 6, 7, 8, 9. 9 positive outcomes are there and the remaining 5 are negative outcomes. So the probability of getting a yes outcome is obviously plus and minus means the positive and negative outcome, sir, Anas sir. I hope that is clear. That is a particular representation used in that particular video. That's not something that is a standard. I cannot tell that it is a standard representation. It should have been yes or no, actually. It's true. I mean, it's a bit confusing, but you can use it as yes or no. And if you have multiple classes, whatever is a class outcome, that particular class name can be provided there. Okay, since it is yes or no, they have conveniently used it as plus or minus. Okay. So we have 9 positive and 5 negative outcomes, or 9 yes values and 5 no values. So I'll just indicate it here. It is yes, and this is no. Some issue. Okay. So when you compute the probability, as I showed, for computing the entropy, you should have the probability of each class. So here it is 9 by 14 for the positive class and 5 by 14 for the no class. So you can compute the entropy as 9 by 14 into log 9 by 14, 5 by 14 into log 5 by 14, and a negation will give you the proper total uncertainty for the entire data set. Okay, so that is the case with the entropy of the whole data set. Now, this entropy is common to every attribute. You don't have to compute it attribute wise or feature wise. This is computed once and we'll be applying it for the whole set of attributes. Now, what we are trying to do is we are trying to compute the gain for this entire data set given each attribute. We are going to compute the gain for the entire data set given this each of these attributes. So initially we'll start with outlook. Outlook is the first variable. So we are starting with outlook variable and we are trying to compute what is the gain. Fine. So we'll go step by step. So the formula for computing gain of the entire data set with respect to a particular attribute is the entire entropy minus summation of a variable. So before going into this variable, we'll just see how the second part is computed. Entropy of the data sample given each value. This stands for each value. So right now we are looking into outlook. So value V stands for the different values that is given in this particular column. So outlook has taken how many number of values? Unique values. It has taken 3 values: sunny, overcast, and rain. So you have to compute the entropy for the data set given the outlook variable and for each of these value, sunny, overcast, and each of the unique value. Again, the formula for entropy remains the same, but the total count is different here. How does it differ is what we need to see. Now I'll just show you how it is split. So when you're looking into the value sunny alone, you have to consider the subset of that particular data set and compute the same entropy or apply the same entropy formula onto this particular table. Even though you can't follow in the first round of explanation, we'll explain this once again. We'll just quickly recap. So this will be clear. So in the first round, you might feel that, okay, there are a lot of steps. It's not like that. It's an iterative process. Whatever you did in the first step for computing the entropy of the entire data set, we are going to repeat this for subsets for each attribute. Then we'll be eliminating attribute and we'll repeat this. Everything is a repetition, but you might take time to to keep it in your mind or to understand or to find expertise in it. Okay, so we'll repeat it once again, you'll understand. So what you're trying to do is, when you're trying to compute the entropy of the feature outlook, we have 3 values there. So you are going to visualize the data set as three subsets. One with the sunny value, one was rain value, and one with the, what was the other value? Sunny, rain, and overcast. Rainy and overcast. So these are the 3 sets of values. So first we are going to look into sunny alone and we'll see how it is computed. Okay. So in sunny, you can see that how many positive and negative outcomes are there. That's what we are trying to focus on. For the entire data set, what did we do? For the entire data set, we found out how many positive and negative outcomes are there. Similarly, for this particular data set, when you are computing the entropy, can someone just tell me how do you compute it here? What will be the probability that you get a yes value here? You'll be posting in chat, right? I cannot see it. 2 by 5. Yeah, 2 by 5 for yes value, and for no, it will be 3 by 5. Right. So when you computed entropy for the entire data set, it was 9 by 14 because we had the entire number of rows. Here we have only 5 rows that we are focusing on. So it is 2 by 5 and 3 by 5 and the same formula reapplied. That is what is done here. I hope you can now understand this formula. 2 by 5 log 2 by 5, 3 by 5 log 3 by 5, and the negative summation will give you the value 0.971. This is for one value, sunny alone. When you repeat it for overcast, you have to formulate the sub data set for overcast. You can see that there are 4 rows for overcast. And how many yes values and no values are there? 2. All the values are yes, which means that it is there is no uncertainty there. That's why when you apply the formula, you can see that you're getting the value 0. As you people told that entropy should be ideally 0, which means that there is no uncertainty, which means that whenever you have an input data point with the value overcast, you can directly say that the outcome is yes. You can play tennis. There is no uncertainty there. So when you apply it into formula also, you're going to get 0 as the value, since all the outcome for the particular value overcast is yes. Is that clear? So just understand that whenever you get a value, just try to understand that also, like why the 0 has come, because everything is yes. When you apply the formula also, you're going to get the same. 4 positive values and 0 negative values, you're going to get the value as 0 when you apply the computation. Now moving on to rain, you're computing the entropy for rain. You can see that there are 1, 2, 3, 4, 5 rows are there, of which 1, 2 values are no and 3 values are positive. So accordingly, you have the formula for entropy for the rain part alone, and you'll be getting a value 0.971, which is both are same, because you have 3 and 2. There it was 2 and 3. That's all. That's what the only difference was. Number of rows is same, 5. So that's why the probability of entropy of rain is computed. So what all did we compute now? We computed the entire entropy. We are trying to find out the information gain for a particular attribute, which we have chosen as outlook. There we are trying to find out for each value. For each value, we are finding out the entropy. The same formula is applied. Now, the gain formula is the most important one, which we are trying to apply these values into. So what is the value there? What is the formula applied there? Entire entropy minus, you're going to find out a summation over all the values. So what for the first term? The first term is nothing but what is the probability that you have a value sunny? What is the probability that you get a value sunny? Or what is the probability that you get a value rain? What is the probability that you get a value overcast? That is what is the formula here. Okay, so each value in the attribute that you are speaking of, we are trying to find out. Until now we were talking about the probability of yes or no. Here we are trying to find out the entire probability of that particular value itself appearing. So sunny, you know that it has appeared 5 times. Then rain has appeared 5 times. Overcast has appeared 4 times, right? So the probability is going to be 5 by 14, 4 by 14, 5 by 14. Clear? So S by this particular term is nothing but the probability that that particular value itself is appearing, and once that value is addressed, you place the entropy of that particular value. Entropy computation is based on the outcome variable, yes no computation, multiply it, and summation, we find out the summation, subtract it from the entire entropy of the data set. That will give you the information gain. So here for this particular outlook attribute, you have got the gain value as 0.2464, which I'm not practically computing, but these computations are actually easy. You just have to understand the steps. So I might ask, if I ask you to do for a particular temperature value, we can just try and we'll just verify these values. You need not compute the entire thing, just try it for these values. So before that, I'll quickly recap once again, okay, don't worry. So how many of you understood the flow? Like, what we try to do is we try to find out the information gain of this particular attribute. That's all is what we have tried to do now. Until what we have told now, have you all understood? I'll repeat once again, or maybe after that we'll quickly take a minute to talk about it. What do you prefer? Chat. So what we're trying to do is, after each of this gain value is computed, what do we have to do? We have to find out the attribute value which is providing the highest gain. Okay, so no answers, nothing. Why do we take negation? Negative is taken, I think log of that values will already give you a negative value, because probabilities are between 0 and 1. When you apply log onto these probability values, it will be negative, already negative. Okay, so just for that negation to be avoided, we are taking the entire negative. Or okay, maybe negative indicates uncertainty. Not like that. I'm not sure, because when you apply negative, log value will again give a negative value. So you need a positive value for performing this computation and the gain to be higher. So that is what the entropy formula actually suggests. With negation itself, it comes. What I understood is, for the logarithm of 0 and logarithm value between 0 and 1, it already will be negative. So you will get a value that can be compared. Otherwise, everything will reverse. If it is a negative value that you're getting as output, you will have to focus on the, like when you're going for checking the lesser value, if you're getting a negative value, you have to go for the greater value. So everything will be reversed. So that's why I hope you're going for the negative computation. Yeah. So should I just quickly recap, or you have understood what the flow is? So if I'm okay, we'll just do along with the next problem, next attribute. It is temperature. So first thing is, you're computing the entropy of the entire data set, which we need not do again because we have already computed it in the previous step. So entropy of S is something that you need not do it again. But how do you compute the entropy of the value hot? Okay, I'm not sharing that screen. Just are you interested in trying out together? Like just for hot, can you compute and tell me what is the entropy value? I'm not asking the final output, just the entropy of the particular value hot. How many entries are there and what value you are getting? Actually, it's too simple because there is no much uncertainty there in that particular column. You can try out and let me know. Once you try for just one example or one attribute, it will be clear. If someone gets the answer, you can pause. I'll just wait for 1 minute. Otherwise, I'll move ahead. Yeah, yes equal to 2, no equal to 2. Fine. Then how do you compute the entropy? You can refer the previous example. Values outlook I have shared. How did we do? 2 and 3 was the value. So here 2 by 2 might have to be taken. Just I mean 2 by 4. Yeah, 2 by 4 is right. So what did you get as the answer? You might have got it as 1. Did you get it as 1? 2 by 4 log 2 by 4 minus again 2 by 4 log 2 by 4 minus 2 by 4 log 2 by 4 minus 2 by 4 log 2 by 4. You might have got it as 1. What does 1 indicate? 0 is in a state that there is no uncertainty. 1, which will mean that there is complete uncertainty, right? Because equal chances are that it can be yes or no. That is the situation. So that's why you get the value as 1. And if you're computing the okay, probably you all are stuck with log computation. That's why the final answer is not coming up. Still okay. I'm fine with that. At least 2 by 4. Somebody has told. So, I mean, Vidya ma'am has told. Sorry. So when you're moving on to entropy of what is the next case? Hot, mild. How do you compute the entropy of mild? Again, just that fraction will give me, fraction will do. In mild, you have 1, 2, 3, 4. 4 yes and 2 no, I think, for mild. 4 yes and 2 no. So you can compute it as 4 by 6 log 4 by 6, 2 by 6 log 2 by 6, and you'll be getting the value as 0.9183. Now entropy of cool again. We have 3 cool, no, 4 is there? 1, 2, 3, 4. 4 cool entries are there, of which 1, 2, 3 yes and 1 no. 3 yes and 1 no. Right? 3 yes and 1 no is there. So 3 by 4 log 3 by 4, 1 by 4 log 1 by 4. That will give you the entropy of cool. Now, how do you apply it into the final formula? Entropy of S, that is the entire entropy of the data set, minus you have to have the summation, of which the second part is already known to you now. First part is the probability that each of this entry appears. So hot appears how many times? 4 times. So it is going to be 4 by 14. Then mild appears 6 times, 6 by 14. Then cool appears again 4 times. So it is going to be 4 by 14. You multiply it with the corresponding entropies, find the summation of it, subtract it from the entire entropy. You'll be getting the final value as 0.0289. 0.0289. So now is the process clear when you did it for the second attribute, temperature? Yes. Vidya ma'am has replied. Anyone? Anyone else? Have you understood the process? Okay. Thank you, ma'am. So once you compute the entropies, so imagine you have to do it for you have to do it for humidity and wind. So for the four attributes that you have in your data set, you have to compute it, and you have got the values of these forms: 0.2464 for outlook, 0.0289 for temperature, 1516 for humidity, and for wind you have got it as 0.0478. As said from the initial intro part of the decision tree, I told that gain is the information gain and entropy is different in a way that entropy will measure the amount of disorder or impurity, but gain measures how this uncertainty is reduced after splitting the data using a particular attribute. So gain should be on the higher end. So which attribute will you choose for splitting the tree? Here the information gain is highest for outlook. Am I right? Yes. So information gain is highest for outlook. So we'll be splitting using outlook. So the 3 values that outlook has taken is sunny, overcast, and rain. So this is how we are going to split the decision tree based on outlook. You have not reached the final decision tree. You have just found out the root node. That is why I've told in the initial part itself, decision tree computation process, it's a bit lengthier, although the method is iterative. If you're writing an algorithm for this, it's actually pretty easy. The lines of code will be less because you're doing the same thing again and again, but the number of iterations might be huge. So when you're doing it in computation, mathematical computation, you might have to perform a lot of steps. So right now we have found out the root node outlook, and it has 3 set of unique values: sunny, overcast, and rain. The peculiarity of overcast is that every overcast values lead to the value yes. So when you have overcast in your data set, it will directly lead to yes. You have just 4 positive outcomes or 4 yes outcomes. So one more thing that I left to mention is that here we are computing for just the entropy for just positive and negative. Again, I told that this is not restricted to a binary classification problem. If it is a multi-class classification, what will happen? You will have many more terms, many more of these terms. How many number of classes are there? That many number of terms will be there. That will be summed up and the negation will be applied. Okay, I hope that is understood. I did not specifically mention, but that should be part of the process. If you're having a multi-class classification problem, you should be able to extend this into multi-classification. What is the difference between multi-class and binary classification? I hope that is known to you, right? Right? Binary and multi-class classification. I think everyone is now fed up or due to decision tree or binary class. If not, I'm just, yeah, okay. If not, I'm just mentioning it. In binary classification, as the word suggests, binary, you just have 2 classes, yes or no. That's more common. We tend to have a have data sets that are more commonly aligned to binary classification. The algorithm or the loss functions, those things actually is different for binary class. Specific to binary classification, we do have different approaches. That is why we learn it as two types, binary and multi-class. Although binary also comes under multi-class, right? You have more than one class, so it actually is multi-class itself, but binary is a special case. Okay. Then we have multi-class. Multi-class classification is when you have more number of output classes. Here we have just two. If you're trying to classify some data set into three fruits, apple, banana, and orange, or uh, more than three or four animals, cat, deer, dog, and giraffe. In that case, it is multi-class classification. So the same formula has to be extended to multi-class. For each class, you will have this probability computation and the summation. That's the only difference. There is no much rule-wise differences in when you're extending binary to multi-class when it comes to decision tree. But when it comes to deep learning or other algorithms, you may have to address the multi-class classification as a separate problem when you compare it to the binary classification. Okay, we'll come back. So when you have the different gain values here, we are going to choose outlook as the root node, and we'll be formulating the root node in the sense splitting node, and we'll be creating the first level of decision tree. And in the overcast value, you can see that there is no uncertainty, it directly leads to yes. But when you look into sunny and rain, values, these set of rows are the rows that corresponds to sunny, these are the rows that corresponds to rain. You may, if you want to just verify it, you can just verify. For sunny, I had actually created a subset. You can see that it is 1, 2, 8, 9, 11. The same has been marked there. 1, 2, 8, 9, and 11. And you have the rain part where you have 4, that I'm not going to go back and verify, 4, 5, 6, 10, and 14. These are the rows that corresponds to rain. Overcast has the values 3, 7, 12, and 13. Those are actually certain. We need not split it again. That is what the meaning is. You don't have to split it again. Whenever you have the value overcast, you can directly lead to the value yes. That is, you can play tennis. Now we have to address the other two uncertain cases, that is sunny and rain. So how do we address it? That is what the next step is. So we'll just look into sunny first. 1, 2, 8, 9, 11. So you can see we have chosen those rows 1, 2, 8, 9, 11, and we have represented a subset there. Any other peculiarity that you see there? What else have you done there? Like we have chosen the subset 1, 2, 8, 9, 11. Any other change in tree? Change in the data set? Anything missing? You can see that the splitting node that we have chosen, outlook, that is removed from there. Okay, now we need not process outlook. Outlook is over. Outlook is processed. We found out what is the gain. We have split it already. So that splitting node is already taken into consideration, and we are taking outlook as the splitting node. And now we don't have to consider outlook again. Next, what we are trying to do is the same process is repeated with this particular data set. Now you consider this itself as the whole data set. You have to start from computation of the entropy of this entire data set. Then you have to go for each of the attribute, which should be the splitting node there. We don't have a splitting node at this point, right? At this point, we don't know what splitting node has to come here. Here also, we don't know which splitting node has to come. So with respect to sunny and with respect to rain, you have to find out two splitting nodes. We start with sunny. For sunny, we are choosing these particular rows, and we are starting with the first attribute, temperature. So what do you have to compute first? First, you have to compute the entire entropy for the particular subset sunny. Okay, so that will remain the main term here. When it was earlier it was for the entire data set. Here it is for conditional to the value sunny for outlook column. Okay, so when you're computing the entropy for sunny, what will be the case? You have 3 no's for this particular entire data set we are talking about. So we have 3 no's, 2 yes. So we'll be computing the entropy as 2 by 5 log 2 by 5, 3 by 5 log 2, 3 by 5. Those will be the terms. You'll be getting an entropy value. That will be your global entropy for each of these gain computation. Then you have to what are the individual values for temperature? You have hot, mild, and cold. You have to compute the entropy for hot, entropy for mild, and entropy for cool. But you can see that those are relatively simple computations, because if you look into hot, you can see that for both the hot values, you get the value no, which means that there is no uncertainty, right? So you can plug in the formula, you're going to get the value 0 itself, even if you plug in the formula. Okay, because you don't have a yes part there. Both the entries are focusing on no. Similarly, for cool, you can see that only yes value is coming up. Again, there also your entropy is going to be 0. And for mild, it's complete disorder or complete uncertainty, because one entry for mild is no and one entry for mild is yes equally. So that is the highest amount of uncertainty. You'll be getting the uncertainty as 1. So equally distributed, if you are getting the different classes, you can directly write it as 1, or you can plug in the formula and find out. So when you get the 3 entropies, what next you have to do is you're subtracting the summation of the probability of each value multiplied by the entropy of that particular value from the overall entropy of this data set. So overall entropy is 0.97 that we have already got. Then probability of having the value as hot is 2 by 5. Mild is 2 by 5. Cool is 1 by 5. We have 5 entries. You compute the probabilities of those values appearing, then multiplied with the entropy, and you'll be getting the value. You'll be getting some value. So you can, that is the gain value that you're going to get. From similarly, you have to compute the gain value for humidity and wind. You'll be computing the gain value for temperature initially, then we compute it for humidity, then we compute it for wind. You'll be getting, just imagine you got these 3 values. Those are computed and you get these 3 values. What will be the splitting node there from these 3 values? Yes, as Neetu has rightly said, humidity can be the next splitting attribute. Okay, because it's directly related. Humidity, all the humidity values are directly, there is no uncertainty there. So directly itself, we can say that, but this is part of the decision tree algorithm process. So we are just showing it. Why that uncertainty is not there is even directly found from the entropy computation also. Okay. So from humidity can be the splitting node at this point. So humidity is kept here. The 2 values for humidity are high and normal. That is kept there, and it is directly linked to no and yes. So this part is over. This part of the tree is over. Overcast. This portion is also over because we have reached the final out target variable. Then the splitting is over. We don't have to split it further if the uncertainty is over. Next is for rain, you have to do the same thing. So there, you'll be taking the rows that corresponds to rain, and the same process is repeated. You compute the gain values for each of this attribute, and you can see that wind is the splitting attribute there. You use wind for splitting there, strong and weak, and it is directly linked to yes or no. Okay, and the decision tree is entirely formulated. So the only problem with ID3 is that it has its own issues, because it cannot have missing values, or it cannot have categorical values, and you will have to, I think the share has stopped. But the advantage is that you can use it for multi-class classification as well. Okay. So that is with decision trees of ID3. Is that somewhat followable or clear to you how that mathematical part has to be done? Hands-on, from what Suchitra ma'am has told, she will be taking it on 18th when she comes offline. If time allows, I'll just show you a small collab file where I think she has shared the lab schedule also. So I had prepared a small collab file. We'll do that if time allows in the afternoon, hands-on session. So you can be more, you can do it alongside if time allows, because in the afternoon session, I'm planning for the neural networks part. It might take time. Okay. So this is what with the decision tree parts. If you get a new problem, also the same thing has to be repeated. Just understand the formula for entropy and information gain, compute it at each and every step iteratively. So until you find out the final target variable coming up without any uncertainty, you will have to repeat this process. Okay. So shall we move on to what was actually assigned to me today, unsupervised learning? We'll start with that. Yeah. Okay. I'll just share this. Hope my screen is visible, right? Screen is visible, right? I've shared a slide. It's a different presentation. That's why I just wanted to confirm. Uh, can someone just confirm? Is the screen visible? You can see it here, but then, yeah, ma'am.
It's visible, ma'am. Visible, ma'am.
Okay, so moving on to unsupervised learning, as we discussed in the intro part, you will not, I mean, you all are already aware of it. We won't be having any labels associated with the data set that you have. That is a peculiarity. So the popular algorithms that comes under unsupervised learning is most popular one is the clustering algorithms. Then we have association rule mining and associated autoencoder learning and all is there, but we won't be going into deeper aspects of that. We'll be learning, I mean, as part of theoretical machine learning that we have to learn, we'll start with clustering. We have to understand the problems, like how the computations are done in the clustering approach. In clustering itself, we have different types. We'll just see one example from each of these two types, and then we'll move ahead with the remaining contents. So we'll be looking more into the clustering aspect. So clustering itself is the one that we just now defined. From the term itself, it's clear that we are trying to group the data points based on similarity of the data points or similarity of the features of the data points. So we have different types of clustering algorithms. One is partitional algorithms, or the algorithms that focus on partitioning the entire data set based on some distance measures. Second. Based on some distance measures. Then we have hierarchical algorithms, where again we are trying to divide the entire data set into a tree structure in a hierarchical fashion. Whenever we talk about hierarchy, it itself shows that there is some tree structure hidden, right? Some hierarchy is there. There is some root node. There is some child nodes that comes from the root. That's what a hierarchy means. So we have hierarchical algorithms. We also have different kinds of mixture of Gaussian algorithms, but we will be focusing more on to partitional and hierarchical algorithms. So partitional, in the sense, the entire data set is partitioned into different clusters based on the number of clusters that we assign, or by finding out the optimal number of clusters. That is the case with partitional algorithm, directly based on some distance measures. Okay, but when we look into, so the most popular example for partitional algorithm is k-means. But since you have learned KNN, k nearest neighbor, almost the same concept is being applied here. Although the label is not there, the concept is almost same. You have learned KNN in yesterday's class. K
Yes,
nearest.
ma'am.
Yeah.
Yes.
Yeah. So the same concept, I would say that it's the same concept, but just that the label part is missing. You are computing the distance between the neighborhoods, and there is a cluster centroid here instead of the label there. That's the only main difference. So we'll look into it, how the computation is done. We'll see that. That is the case with k-means. K-means is the most popular example for partitional algorithm. Then we have hierarchical algorithms. It's also called agglomerative hierarchical algorithms, wherein, so I'll just show you. In hierarchical agglomerative algorithms, what we do is you're looking into the entire data set as a single cluster, and sorry, just trying to write. And you either split it into subcategory subgroups in a, like as in a tree structure, and you reach the individual points as different clusters. That is one method. That is called the top down approach. You also have the bottom up approach. That is how we start is that we consider each data point as individual data point, group the data points based on some distance measures. So here, if I'm trying to group C and B individual data points into BC, it means that C and B was somewhere closer in some distance computation. So when you compute some distance and find out that there are closer data points, you group it into different clusters. Then you compute the inter-cluster distances. Again, you group it. Wherever that value is less, the distance is less, you try to group it and formulate the entire data set at the top point. So if you want that only 3 clusters need to be formed from the data set, you decide a particular point in this hierarchy, and
take the resultant groups from that. That's what is happening. So the divisive, or it's one is divisive and one is the other way around, that is hierarchical or agglomerative. So you have two approaches just that you need to understand in the hierarchical kind of clustering. We have top down and bottom up approach. So top down means you start from the entire data set, then you split it. That is called divisive. You split it and then formulate the individual until you reach the individual data point. And in the agglomerative, it's the other way around. You start from individual data points, you group it based on some distance measures, group the clusters, and then you reach the entire group of data points. So at a point where you need, suppose you need 3 clusters, you'll be choosing it from this hierarchy, where you find that suppose you need 3 clusters, you can see that these 3 are the uh, this particular hierarchy is the point where you can get 3 clusters. So those 3 clusters will be chosen. So if you need more than that, if you need 5 clusters, or if you need 1, 2, 3, 4, 5, 6, 7, 8, 8 clusters, it means that this is the most ideal level at which you have 8 clusters. You just have 8 data points, so that will be chosen. But the process is done in an entirety. You start from the entire data set to the individual data points, or you start from the individual data point and reach the entire data set. Top down and bottom up approach. So when you move on to the aspects of these clustering algorithms, you have the distance function, which is very important here. In clustering, the distance measures are very important. So Euclidean and Manhattan is the ones that you have to keep in mind, because we'll be using it interchangeably. So I hope that difference is clear, right? What is Euclidean distance and Manhattan distance? Can someone just tell me? Difference between Euclidean and Manhattan distance. Are you posting? Actually, I'm not able to see. Okay. Since it is too familiar, not answering, or is there any confusion? Like, if required, I've put it in slide. We'll just discuss about it. Euclidean distance is the shortest distance. I hope the formula is also clear to you. If you have 2 points x1, y1, and x2, y2, difference between x2 and x1 and y2 and y1, the square of the sum of those two will be the square root of the sum of those two will be the Euclidean distance. That is a very popular formula that everyone knows, I hope. X2 minus x1 whole square plus y2 minus y1 whole square, and the square root of that will give you the Euclidean distance. It is derived from the Pythagoras theorem, actually, the hypotenuse value of these 2 points. That distance is what actually it indicates. So it is the shortest distance. But when it comes to Manhattan distance, was there anything that someone has told? Yeah. Coming to Manhattan distance, it's the absolute difference that we are talking about. So if you need to find out the difference between these 2 points, x2 has a value here, x1 has a value here, this absolute difference will be considered for x part, and for y, this distance y and y1, y2 and y1, that absolute distance will be considered, and that will be summed up. So it's the absolute difference that we consider. Otherwise, a negative will cause issues. So you're taking the absolute value of x2 minus x1 and y2 minus y1, and that will give you the Manhattan distance. Okay, so those two are different aspects when it comes to the distance measures. So you should know what these two are. We have to use these two in the upcoming clustering algorithm process. Then how do you determine the quality? That is also one important point in clustering. How do you determine the quality of a clustering algorithm? You have 2 kinds of distance measures. One is inter-cluster distance and one is intra-cluster distance. From the name itself, it might be clear. I mean, it's quite obvious. Inter-cluster distance is when you have 2 clusters, what is the average distance between these 2 clusters? For this example that is shown here, what is the distance between partition 1 and partition 2, or what is the distance between partition 2 and partition 3? That is what is indicated by intercluster distance. Intra-cluster distance means what is the distance between the data points inside a cluster. So if you name these data points as D1, D2, D3, the distance between D1, D2, D3 is indicated by the intra-cluster distance, or the average distances between the data points inside a cluster. So ideally, if you want to have a high quality clustering that is performed on your data set, you generally say that the ideal case is inter-cluster distance should be maximum. That is, the partitions that you have made should be highly distinctive of each other. It should be differentiable, very much clearly distinguishable, which means that the inter-cluster distance should be maximum, and the intra-cluster distance, which means the data points within a cluster should be at a very minimum distance, extremely minimum distance. That is what is ideal for a proper clustering algorithm to have high quality. Okay, so these are the main aspects of clustering points that you need to keep in mind. One is the types, partitional and hierarchical. Distance measures, Euclidean, Manhattan, at least that should be known. Then quality, intercluster and intracluster distance. What these are, how does it determine or how does it help in determining the quality of clustering algorithm? Clear. Then there are other, as I told earlier, mixture of Gaussians. We have different kinds. Then density-based clustering. The by computing, we are not going into deeper aspects of that, but we in this part just keep in mind DB scan when you go for that coding part. You might have to use DB scan and model-based clustering because that also gives good results. DB scan is very much responsive to noisy data. So here what we are trying to do is we are just finding out the highly dense regions and then separate it from the low density regions. That's what we aim at performing, aim by performing density based clustering. So we are not detailing it, but I'm just telling you for your information that DB scan and model based clustering are also that these are actually screenshots taken just for your information. Okay. Then we'll be moving on. We are moving on to K-means algorithm, which is the most important one in unsupervised learning. So the algorithm is you have a set of data points. What we are trying to do is you're finding out initially randomly we are trying to fix how many number of clusters have to be there. That should be hard coded. So suppose you have some 10 data points and you're given with a set of data points. I'll show you an example. You're given with a set of data points. What should additionally be inferred is that you have to fix how many number of clusters are you trying to divide this particular data points into, and accordingly, so suppose you're having two clusters or you're planning to divide the entire data set into two clusters, you should have two cluster centers also taken randomly. Initial cluster centers, which acts as the seed to this k-means algorithm, that will also be taken randomly. So in this example itself, we can see that there is a set of data points 2, 4, 10, 12, 3, 20, 30, 11, and 25. And I'm telling that I'm dividing this into two clusters. That should also be given to you. That should also be hard coded, and particularly in k-means. Two sets of clusters are being considered, which means that the initial seed values for this cluster should also be taken. It can be taken randomly. Any value can be taken. So here for this example, we are taken it as 4 and 11. Okay. So if you had three clusters, if you are assigning or if you are deciding to go for three clusters, you should have three random cluster centers initialized in the first iteration. So that is how we start with. So randomly choose k data points or seeds to be the initial cluster centers. Assign each data point to the closest cluster center. What does that mean? You have initialized three, suppose the entire data points is divided into three clusters and you have three cluster centers. For each data point, what you're trying to do is you're trying to find out the distance to these three cluster centers. Whichever is having the minimum distance, that particular data point will be assigned to that particular cluster. So if I'm trying to take this data point, I'm going to find out this distance between this point to these three clusters. And I found out that the minimum distance is to the green data point, which means that this particular point gets assigned to the green cluster. If I'm taking another data point, this particular data point, and I'm finding out the distance from this data point to green, blue, and red, obviously it is having lesser distance to blue data point. So that will be assigned the blue label, not label, blue, that will be assigned to the closest cluster, which means that blue cluster. Okay, so that is what is being done in the second step. So once the grouping is over, initial grouping is over, we know that we have initialized some cluster centers, which is randomly initialized. There is no logic behind that. So these grouping may not be an ideal one. So you have to have an iteration. You may have to recompute the cluster center, right? So how do you recompute the cluster center? You have to find out new cluster centers. Cluster center means when you have a group group of data points, you just have to average those data point values and find out the cluster center, find out the average or the mean value of those data points, which will give you the new cluster centers. So after one iteration, you will end up with new sets of cluster centers. And when do we stop this? Again, you'll be finding out the distance from all the data points to these clusters, and you'll be assigning those data points to these any of these clusters. Again, you'll be computing the cluster center. So, what is the convergence criterion? It said that in the fourth step, if a convergence criterion is not met, you'll have to repeat this. So, what will be the convergence criterion? Any idea logically? The cluster center has kept changing, right? Initial cluster center was computed. Then we computed the data point distance to each of these clusters, assigned to each group. Again, computed the cluster center. You're checking whether the convergence criteria is met. Otherwise, you're again computing the distance and assigning to different clusters. Again, cluster center is computed. So, what do you think might be the convergence criterion? Yes, if no change in the cluster members, which means that the cluster center does not change. When there is no change in cluster center computation, or if there is no change in the cluster assignment, you can say that your model or the algorithm has converged, and you can stop the iteration process. You have formed the k-means clustering algorithm. Okay, so here you can see that the convergence criterion is no reassignments of data points to different clusters, or there is no change of centroid. Centroid is nothing but the cluster center that we are computing, and there is minimum change in the sum of squared error. That we'll see that what that is when you learn about the elbow method and all that. It will be clear. So disadvantage of k-means algorithm is that you have to clearly specify how many number of cluster centers have to be there, and the hard assignment, which means that you're assigning each of the data point to the cluster based on the distance algorithm. So that is also a hard assignment. Initial assignment is actually a hard assignment. So if the seed value that you have taken is not that good, you may not get the exactly same clustering ineffectively. Okay, so when you are giving problems to students as part of the exam point in the exam point of view, you will be providing the initial values. Then we have the Euclidean measure distance, which has its own limitations in certain scenarios where your number of features are more. If you have just two features, or if you have just one or two features, your distance computation might be okay. You just have two values. With that, it's fine. If it is more, you can compute, but the distance value that it gives in a high dimensional plane, when you're relying on the Euclidean distance, it has its own limitations. The distance computation, or the distance actually that data point where it lies, or the cluster assignment may not be exact or may not be accurate. Okay. So in categorical data, k-means is not an ideal choice. You have to go for other options. So we'll just see how this example is worked out. It's 10:50, but we'll just see how this example is worked out and then stop for the break. Will that be fine? Yes. Okay. So here the data point peculiarity is that, what did we say? We told that we have only the input variable. We don't have the outcome variable. So this is in such a way that you just have one column. It's like this. You have just x. You just have x value, and you have a certain set of values there, 2, 4, 10, and so on. This is how the data set looks like. So if you have more features, you can have it as x1, then you have x2, second variable might be there. If you have more variables, x3 will be there, third dimension will be there, but keep in mind that y is not there. Okay, so these we'll just start with a data set which has just one feature, so that you'll understand the computation. Then we'll move on to a two variable example. I'll just quickly show that and leave. But with that, any high dimensional data set can be handled. Okay. So the initial cluster centers, as I told, is 4 and 11, and you have these set of values as told in the example. So these are the cluster centers. So initially, just keep in mind that you'll be drawing a table of this form. You'll be marking the cluster centers, M1 and M2. So here it is going to be 4. It's going to be 11 here. So what will be the what are you trying to compute is from each of this data point, you are going to compute the distance from this data point to this cluster center. Each of these cluster center. So from 2 to 4 is computed and written here. From 2 to 11 is computed and written here. From the data point 4 to the data point 4 is the distance between 4 and 4 is computed and written here. Distance between 4 and 11 is computed and written here, and it goes on. So since it is just one variable, if the direct subtraction will give you the value result. Even though it is Euclidean distance, you need not go for the square root x2 minus x1 whole square computation because you just have one variable. So if it is x2 minus x1 whole square, what is it? X2 minus x1 whole square, the whole root, which means that it's just x2 minus x1 itself. So you don't have to go for the Euclidean computation. That is the easiness of having a one feature data set. So 2 minus 4, absolute value, that's going to give you the value 2 here. Then 2 minus 11, it's going to give the value as 9 here, right? 4 minus 4, it's going to give the value 0 here, which is already marked. Then what is the next value? 4 minus 11. 4 minus 11 is going to give the value. Okay, and so on. So you'll be filling the table of that form. I'm not repeating the entire step. It's just a matter of subtraction. I hope you have got it. M1 and M2 is the cluster centers 4 and 11. You're computing the distance from each of these data point to these two cluster centers and filling it in the table. So how do you assign a cluster here? How do you assign which cluster that particular data point belongs to? What needs to be compared? What will be the cluster assignment for the first data point? Imagine the clusters are C1 and C2 corresponding to this particular centroids 4 and 11. So then what will be the cluster assignment for this? You found out that the distance from the data point 2 to 4 is 2. You found out the distance from the data point 2 to 11 is 9, which means that the data point 2 is closest to the centroid 4, which is the first cluster. So you're going to assign the first data point to cluster 1. Is that clear? I'll just show it for the second data point 2. For second data point, since it is already the cluster center itself, you need not bother, you need not even compare. You can directly assign it to cluster 1 because that itself is the cluster centroid. Okay, so C1. Then we have the third data point 10. 10, you can see that the distance from 10 to cluster center 4 is 6. Distance from 10 to cluster center 11 is 1, which means that you'll be assigning the data point 10 to cluster 2. Cluster 2. Okay. Is that fine? Yes, 10 to C1. 10 to C1. 10 to 2. Yeah, 10 to 2. Neetu ma'am, I mean, I didn't get what you wrote. 10 to C1 means 10 to actually C2. Okay, fine. Any other questions were there? Less distance, minimum distance. Okay. Then, so likewise, you can do the entire assignments. You're going to get it of this form. You can just quickly verify whichever is the lowest value that will be assigned. So here it is C1, here C1. Here when you compare it is C2, here C2. 1 and 8 when you compare it is C1. 16 and 9 C2. 26 and 19 C2. 7 and 0 C2. 21 and 14 C2. So this is going to be your cluster assignment after the first iteration. Okay. Now the next step is, as said in the algorithm, what we are trying to do is we are trying to find out the average or the mean value, centroid value for this, for these two clusters. So C1 assignments corresponds to 2, second data point 4. Then we have this data point where C1 appears, C1. Okay. So how do you compute the centroid? It's quick and simple. It's just the average. So 2 plus 4 plus 3. These are the cluster ones. 2 plus 4 plus 3. It's going to be 6 plus 3, 9. 9 by 3 is going to be 3. So your new centroid is going to be 3. one more centroid should be there, right? So that is for the second cluster. New centroid for the first cluster is going to be 3. New centroid for the second cluster is going to be 10 plus 12 plus 20 plus 30 plus 11 plus 25. Since there is just simple addition, I'm not asking you to do, it's just 108. Okay, I tried it out, that's why 108. And you have how many data points? 1, 2, 3, 4, 5, 6. So 108 by 6 will give you, I think, 18. Okay, so your new cluster centroids are going to be 3 and 18. Okay. Accordingly, what you have to do? What should be done next? Can someone help me out here? What should be done next? We have got new centroids. So this entire process has to be repeated again. That's what we have to do again. Initially it was 4 and 11 that we have blindly taken. So next is 3 and 18, which means that your M1 is going to be 3, M1 is going to be 3, M2 is going to be 18. Some problem with my stylus. 18, and accordingly you have to find out the distance from each of these data points to M1 and M2, the same process. So what is the distance from the data point 2 to M1? 2 minus 3, it's going to be 1 here. Then to M2, 2 minus 18 is going to be 16 here. So the cluster assignment remains the same. 2 and 16, 1 and 16, when you compare it as C1 itself. Then you have 4 minus 3, 1. Then 4 minus 18, it's going to be 14. Cluster assignment again remains the same, C1. Then 10 minus 3, it's going to be 7. 10 minus 18, it's going to be 8. So cluster assignment changes from C2 to C1, it seems, right? Or did I make a mistake? It's C2 itself. What happened? 10 minus 18, it's going to be 8. 10 minus 3, it is 7. So yeah, C1. Actually, it should be C1. Am I right? This should be C1. There was a mistake here. Yeah, no, this is the old cluster. This is a new clustering, correct. C1 is correct. Okay, sorry, I got misled. Then again, you just repeat it for the entire process. You can see that in certain cluster assignment, there will be variations. Okay, so now itself we got a cluster assignment variation. You got it as C1. We'll just see the new clusters. Here, the distance computation has to be done in the same way. And you're assigning the clusters wherever the minimum value appears. So for this point, you can see that there is a difference. Any other point where difference has appeared? No. Here C2, C1, C2, 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 all are same. So only one place we can see that there is a cluster assignment difference, but still it means that we have not, the algorithm has not converged. So what we have to do is again repeat the process. Again repeat the process in the sense, for the new clusters formed, you have to compute the centroid value. You have to compute the mean or centroid value and then again find out the distance. This has to be repeated until the cluster has no change. So for these two sets of clusters, I'll just quickly show you what is M1 and M2 values. It's going to be 4.75 and 9.6. Those are the mean values. How do you find out this mean value? Any doubts in that? Did you get what k-means algorithm is? Is there any doubt? How was this centroid computed? How did we get M1 and M2 as 4.75 and 19.6? Shana has replied as a yes. How did we compute that, M1 and M2? Average. Average of each of this cluster. Okay, simple concept. So once this is computed, again, we are going for distance computation. Once the distance is computed, you're assigning clusters. So in this particular iteration, I think from here on, there is no change. Yeah. So here, with this particular data point, 7 and 25, not actually 7 and 25, the previous one. Yeah. In the previous iteration, it was 7 and 25, and you apply the clusters, new clusters and old cluster. And afterwards, when you compute the new cluster centroids and you see the cluster assignment, you can see that it remains the same. So this is the point where you stop the iteration and you decide that which all points comes to cluster 1 and which all points are
part of cluster 2. At this point, you can stop the clustering process. When you see that clusters, the old cluster assignment and the new cluster assignment are exactly the same, or the cluster centroid has not changed. Okay. Now, the example that we saw, with this I'll stop. Like you have I know it's 11. I think it's a tea break time, right? I'll just quickly tell this. The example that we saw right now is for single data point or single feature data set, single dimension data set. Here you can see that in this particular example, there are 2 dimensions or 2 feature values. So accordingly, the distance computation will change. We'll just quickly recap and discuss in 5 or 10 minutes after the tea break how this 2 data point has to be addressed, and then we'll move on to the hierarchical clustering part. Okay. Is that fine?
Okay.
Shall we come back
Yes.
after the break?
Okay, ma'am. Thank you so much.
Thank you.
The session 1 was so crisp and clear, ma'am.
Thank you.
We understood the concepts.
Okay. If should I go a little bit faster or slower, you can just tell me. Okay. I mean, if I'm fine with that. I thought.
Fine, I guess.
Okay.
Waiting for the response from others.
Okay, you can inform me even after the break, and I'll do it accordingly.
Okay, ma'am. Thank you. We'll have a short break, and we'll be back by 11:15 sharp.
Thank you.
Thank you, ma'am.
Thank you. Hello all. Can I start or should we wait a few more seconds? Dhanya ma'am, can I start? Elizabeth ma'am?
Ma'am, one more minute, ma'am.
Sure. I just wanted to confirm whether you were waiting for my, but that's fine.
Yes, ma'am. Sorry.
Just let me know when I can start. Thank you.
Okay. I'll inform you, ma'am.
Sure.
It's okay, ma'am. Shall we start the next session, ma'am?
Yeah, sure, ma'am. I was waiting for
Okay. You were waiting. Here, tea was late to arrive, ma'am.
No
That's
issues.
why.
No issues. No, I thought I will get an intimation and then start. I'm ready, ma'am. It's fine.
Okay. Everybody is back to seat, ma'am. We'll start.
Okay, ma'am. Thank you.
Okay. Thank you. Over to you, ma'am.
Thank you. So I'll just share the screen and we'll continue. 1 second. Okay. Hope the screen is visible.
Yes, it's visible.
Okay, thank you. So we were discussing of we began the session. We'll just quickly recap. We started off with decision trees, which is part of supervised learning. Don't get confused with unsupervised, because I was told to take unsupervised today. But then since decision tree was not covered in yesterday's session, we started off with the supervised learning itself. Decision trees were covered, and the ID3 algorithm with an example we tried out. I hope that has followed. Then we started off with unsupervised learning. What all practical techniques are there in unsupervised learning? Basically, two ones: partitioning and divisive kind. I mean, hierarchical kind. And both of them has one example each: k-means and agglomerative, which we'll be learning today. Then we started off with k-means and we learned what are the distance measures. In k-means clustering, we did an example with one feature, so that the distance computation was pretty easy and we can directly learn the process. So when you look into 2 points, I'm not doing the entire example, but what difference in computation comes up that we can see now. So this is an example question with 2 features. So how this data set will appear is you'll be having a table. You'll be having 2 features, x1, x2. This is what that indicates. This is x2. First data point is going to be 2, 10. Second data point is going to be 2, 5, and so on. So that is how
this data set will appear, but we are taking it as points and we have represented it here just for the easiness of computation. Okay, so you are already representing it as individual data points A1, A2, A3, B1, B2, B3, and so on. And here we have taken the cluster centers as A1, B1, and C1. Don't look into these numbers. These are actually the final answers. This is just the final answer. When I share it with you, you can refer this for the final answer. You can use this for computation. So A1, B1, and C1, those are taken as the centroid. So from the naming itself, you can see that these are three clusters that is being indicated just for a demonstration purpose. So A1, B1, and C1 is taken as the individual initial cluster centers. So what needs to be done first? What is the first step? You are going to compute the distance from each of these data points into this cluster center. So three cluster centers are there. So as opposed to the previous example, we had just two cluster centers. We have three cluster centers here. So three sets of distance computation has to be done. You're comparing three sets of values while you're assigning the cluster value to the final column. Okay, so these are not the actual cluster centers. As I told, this is a final iteration. Don't bother the values, but just understand the method in which this can be addressed. The only difference is when you're computing the distance from A1, okay, you can ignore A1 because that itself is a cluster center. We'll take A2. If you're finding out distance from A2 to A1, you have the data point 2, 5, and the initial cluster center was 2, 10. So 2, 5 to 2, 10, you have to find out the distance and apply Euclidean distance there. Euclidean distance is square root of 2 minus 2 whole square plus 10 minus 5 whole square. That will be your final distance result here. This is not the value. This is for the final iteration. I'm just telling you that you have to apply the perfect Euclidean distance formula here and find out the distance for each of the cluster center, compare it, assign the cluster. The remaining process is entirely the same. The only thing is the Euclidean distance computation will be now for two variables, two dimension. Okay, there is no other difference. And when you compute the cluster centroid also, the mean value you have to compute for X differently, you have to compute for Y differently for each of the cluster, and that will be your new cluster centroid. Average it, and that will be your new cluster centroid. Is there any doubt in this, doubt in the k-means clustering when it comes to multiple dimensions? So if you have even more dimensions, 3, 4, or 5, the same approach has to be applied. The Euclidean distance computation will have more terms. The remaining steps remains the same. Centroid computation is for individual coordinates of individual features. So for X itself, you will have the centroid computation. Y itself, Y in the sense second feature, X1, X2. X1 will itself have its own centroid computation, X2, X3, and so on. How many dimensions are there? That many number of values will be computed, comma separated, and that will be your new centroid. Is that fine? Should we do this example? I don't think so, but if you insist, I can go ahead with that. Only the Euclidean distance part is different, and the centroid part, instead of restricting it to one variable, you have to do it for the all the features. That's all. Is that fine? Can I move ahead with the next concept, or should we solve this? It's fine. Okay. I'm taking Dhanya ma'am's answer as the representative answer from the group there. Okay. That's it. There's nothing much more confusing here. So we'll move ahead. Now in k-means, as we talked earlier, we have the issue of finding out the optimal number of clusters. We are telling that we are hard coding the hard assigning the number of clusters. Initially itself, for the both the examples that we talked about earlier, we had two clusters in the initial example. In the second example, we are assigning that there are three clusters. We want to group it into three clusters. So that number of clusters into which you have to divide the data set, that has to be assigned earlier. But we don't know which is the optimal number of clusters that is suitable for a particular data set in a particular domain. So there are algorithms for that. So suppose you have chosen 3. You have to find out whether 3 is the actual optimal number of clusters ideal for your data set. Right. So there are two methods for that. One is elbow method and one is the Silhouette method. Elbow method is quite simple in the sense it's repetitive in nature, but still the method is simple. In elbow method, what you're trying to do is you're applying k-means algorithm with the number of clusters starting from 1 to the total number of data points actually, but ideally we'll just top it with 10, 9 or 10, not more than that. So even if you have hundreds of data points, you will just group it into maximum 10 clusters. So you will start from one iteratively to at least 10 clusters. And for each k value in the sense each number of cluster values, you are going to compute something called the within cluster sum of squares. Within cluster sum of squares, which we discussed in the intro of k-means clustering, and I told that we'll discuss during the elbow method. So within cluster sum of squares indicates how tightly coupled is your data points within one cluster. Okay, that is an indicative measure of that. So if this value is chosen for measuring the ideality of your clustering method, you can find out, or you are using this within cluster sum of square method to identify the optimal number of clusters. So for each of these number of clusters, one doesn't require any computation, but for one, which means that you just have one cluster. So you are computing this within cluster sum of square distance. So what does that indicate? From each of the data point, you are finding out the distance from that data point to the cluster center. That is the Euclidean distance. Square it, sum it off. Okay, so that will give you this sum, the first sigma part. You're taking each data point, find out the sum from this particular data point to the cluster center, square it, one value. Summation of each of these data points to this cluster will give you the first measure, and the outside summation, you have to repeat this for each of the cluster. If you have 3 clusters, you have to repeat this process for each of the cluster, and that summation will give you the within cluster sum of squared distance. Is that clear? Within a cluster, you're computing distance from each data point to the cluster center, square it, sum it off, you get the internal sum. You have to repeat this for each of the cluster, that is indicated by the outside summation, which will give you the final within cluster sum of squared distance. Is that fine? So m is the number of data points in a cluster, and n is the number of clusters that you have for a particular data set after applying the k-means algorithm, or for each k value that you take. Fine. So that is the within cluster sum of squares. So what you're trying to do is in elbow method, as I told, for each of the number of clusters that you assign from 1, ranging from 1 to 10, ideally from 1 to 10, you plot the number of clusters against the within cluster sum of squared value. You can see that for generally, this is the ideal case, you get such a kind of graph where you have a line that starts from a very high value. If you are choosing the number of clusters as too low, you'll be getting higher values. If you are taking the number of clusters as too high, obviously the value is going to be lesser. But the thing is, the number of computation that is required for creating 10 clusters might be more. So there should be a balance between these two. Like you shouldn't go for 2 less number of clusters, or you shouldn't go for 2 more number of clusters. So you should find a balanced number of clusters using some method, which is the elbow. One such method is elbow method, in which we focus on the within cluster sum of squared distance. And you find a point. You can see that there is a point where it looks like an elbow. There is a quick shift from the highest value, and it start going into the lower direction. This point, the number of clusters corresponding to this particular elbow point is ideally taken as the optimal value for number of clusters for a data set. Okay, I'll repeat once again. You have in k-means clustering, there is a disadvantage. As we told, we have to set the number of clusters initially itself, right? But there might be an optimal solution for each of the data set. We don't know whether the number of clusters that we have chosen is ideal or not. For performing k-means algorithm, you can go for the elbow method, wherein you iteratively perform this k-means clustering on different number of clusters. You will be writing a code, right? You'll be formulating a k-means clustering for different number of clusters. You compute ideally just go for at least maximum 10 number of clusters. You don't go beyond that. There is no point in grouping beyond 10 and all. For logically, you can think about it. Maybe if it is 100 data points, you can stop with 10. If it is a huge, massive data set, generally we don't go for k-means clustering with massive data sets. But if it is that case, then you can increase this number of clusters. That is still fine. But ideally, for smaller data set, we go for at least we go for maximum 10 clusters. So, but this is not a hard-coded rule. We don't take that, okay, we are supposed to take only for 10, it's nothing like that. So 1 to 10, you're taking in a ideal scenario, and you're computing the within cluster sum of square. We are plotting this within cluster sum of square against the each of the k value. Now within cluster sum of square is computed for each of the cluster. For each of the cluster, for all data points, you compute the distance from the data point to the centroid point, square it, sum it off, you get it for one cluster. You apply for every data point, you get it for one cluster. Then for the outside summation, you are doing the same for each of the cluster. You'll get a huge value for the within cluster sum of squared distance. You are plotting it. When you are plotting it, you get a point where an elbow appears, which means that there is a drastic change from the higher values to the range in which it moves to the lower direction. Okay, so this particular elbow point is chosen as the number of clusters corresponding to this particular elbow point is chosen as the ideal number of clusters for your particular data set. Is that clear? What elbow method is? But repeating this for these many number of clusters manually, it's not a easy task, but we do have algorithms for that. We just write a loop above with different clusters and cluster numbers. The code itself will it repeats and find out it will give you a visualization of the plot, and you can find out the optimal k value. Clear. Now another method, the one method that we talked about is elbow method, which focuses on the within cluster sum of squared distance, and it's going to be huge, right? Now another method is the Silhouette method. Silhouette method. Maybe there are other pronunciations. If people who already know ML, there might be a different pronunciation. I generally pronounce it as Silhouette score. So Silhouette score, again, it uses a combination of within cluster distance and inter-cluster distance. Both are taken into consideration while you're choosing the ideal value. So there is a formula for that, which I mean, you may have to mug it up. Like, I cannot relate it. I cannot tell you how to relate it, but each term I'll just tell you how you can relate it to this formula. So B of I and A of I, you have only just two terms and a combination of that. The difference between B of I and A of I, and in the denominator, you can see that there is a maximum value for among A of I and B of I is chosen. Okay, so what is that? What is this B of I and A of I, and ultimately what is that I? I is for a single data point. So you are going to compute Silhouette score for individual data points, and for each data point, what you're trying to do is you're going to find out the average distance of that point with all other data points in the cluster to which it belongs. That is the intra distance. AI belongs to intra distance. Okay, a single data point you're taking, and you're taking the distance from that data point to all other data points within the cluster which it belongs. Then comes B of I. B of I is nothing but from that data point, you're computing the distance from that data point to all other points in the other clusters in which this particular data point does not belong. You're finding out the average of those distances. That is B of I. So you get the inter distance from that particular data point to all other clusters. So you have A of I and B of I. A is the distance from, I'll show you a pictorial representation. A is the distance from this particular data point to all the data points within the cluster. And B of I is the average of this distance from this data point to all points in a different cluster, not just one cluster. If you have multiple clusters, distances from this particular data point to all these cluster points or data points in which this particular point does not belong to, that is the B of I. Average of that distances will be B of I. Okay, that represents the inter distance, the other one represents the intra distance, and you're finding out the difference between those two, and in the denominator you have the maximum of A of I and B of I. So this Silhouette score you are going to get for one data point when you perform this operation. So when you get the Silhouette score for each of the data point, finally there is a Silhouette score that needs to be computed. You get Silhouette value for each of the data point. So you have different Silhouette scores now, or Silhouette values now. Final Silhouette score is the average of these data points. So if you have 10 data points and you have 10 Silhouette scores, how do you find out the final slot value? It's just the average of all the slot values. Okay. This is done for each of the number of clusters as we did with elbow point. So the method is actually tedious. If you're trying to do is do it in handwritten method in the proper computation way, it is actually quite tedious. It's a tedious process. Here also you have to do this, perform this for each of the cluster values. Now number of cluster values. Okay, start with 1 and here they have shown it till 8. Generally, as with k-means, we can take it to 10. And here also there is a bend that we try to focus on, but it's not like the elbow. There is a point where it reaches the global maximum and then it starts to move to the minimum value. This point is the number of clusters corresponding to this point is what is taken as the ideal value. Okay, so Szilard score, I'll just repeat once again. In Szilard method, you are computing two distances. One is the distance from each data point. Your first thing that you have to keep in mind is you are computing Szilard score for each of the data point. For that, you have two distances. One is from each data point, you are computing the distance from that data point to all other data points within the cluster, as in this diagram. That is A. That is indicated as A. Then we have computation, distance computation from that data point to all the data points in which this particular data point is not a member, to the clusters in which this particular data point is not a member. So that distance is indicated as B of I, and I forgot to mention it is the average distance. It's not the sum of distance. You are finding out the average distance from this particular data point to all other data points. You have A and B now, and based on the Szilard formula, you are finding out the difference between B of I and A of I, inter and intra distances, and the denominator is going to be the maximum of these two. You will get a Szilard value for one data point. This has to be repeated for all the data points. Average it, you are going to get a Szilard score. This has to be repeated for the number of clusters ranging from 1 to any ideal value ranging in the range of 8 to 10. So, and that has to be plotted as with the elbow method. There we were trying to find out a bend as in the shape of an elbow. Here we are trying to find out a maximum value that it goes, and then at that point it breaks and it moves on to the lower range, or it's moving on to the minimum value or to the lower slope. At that point, whatever was the number of clusters that was taken, that is going to be the ideal number of clusters that you have to choose for Szilard, for your particular data set. So that is the way in which Szilard analysis has to be done for identifying the optimal K method. Okay, so there is also another inertia with which you compute the performance or analyze the performance of your k-means or the clustering algorithm that you have applied or the number of clusters you have taken. That is probably done during the hands-on session, where when you run it in code, you can directly see what inertias ma'am might be, Sujitra ma'am might cover it. Or if time allows in the afternoon, I wish to show, just show. We may not be having time to do alongside, but just to show, I might use it in the afternoon session. Okay. So we just finished off with k-means algorithm. So in k-means, what all did we cover? We started off with what k-means is, what k is, the number of clusters. Then with 1 dimension and 2 dimension, we just saw quick examples. The iterative process, when to stop, convergence criterion. Then we saw how to find out the optimal number of clusters based on two methods, elbow and Szilard score. That was the second part. So hope you have understood till now. We'll just take a 1 minute and make sure it's full. All of you have reached here. Okay.
Yes, we could follow, ma'am. It was clear.
Okay. So we'll move ahead with hierarchical clustering. As opposed to k-means, k-means was based on partitional clustering. Hierarchical clustering is, it's not based on like a partitioning based on the distance measures and all. Hierarchical clustering, we need not mention what is the basic advantage from what you have heard till now. What is the basic difference between k-means and hierarchical? Not based on the basic concept, but I'm just asking. One main disadvantage I was indicating for k-means was that we have to mention the number of clusters upfront, right? We have to say that, okay, I'm going to divide it into 3 clusters. Then only we can start the process. But in hierarchical clustering, it's not that way. We need not mention what is the number of clusters. You perform the clustering, and at what level we require the number of groups has to happen, that we take from the final result. That is the case with hierarchical clustering. So in hierarchical clustering, it's not based on the partitioning part. You are creating a hierarchical tree of objects, and then you are applying the based on the distances. Again, a distance measure comes up, but that's in a different method or different algorithm. So we are going to represent the data points finally in the form of a tree structure. This is not a normal tree. This tree is called a dendrogram. DENDRO, dendrogram. Okay, this tree is called a dendrogram, and it's not just a simple tree. It actually is plotted based on some distance value, which actually has to appear here. Based on that, you're drawing this dendrogram. It's not just some random indication here. It's based on the distance value that we are plotting this tree. It's not just simply a tree that you see as part of a graphical structure or decision tree. It's not like that. You have to draw this dendrogram based on this distance measures. Okay, how to compute it, that we are going to see with an example. So different objects are clustered at different levels. You can see that there are certain levels here. Finally, from this example, from the example that is shown here, and you are seeing a dendrogram there, right? It means that initially we had 1, 2, 3, 4, 6 data points: Lisa, Joe, Alan, Max, Caro, and Nora. Based on some attributes of them, maybe their IQ score or something, we are trying to group them. So before trying to group them, we first find out which of these members are very close to each other. We are not choosing any centroid. Directly we are going to find out which of these members are very close to each other. So we might have found out that Lisa and Joe is very close to each other, because that is the first level at which that grouping has taken place. You can see that this is a bit more higher, right? So Lisa and Joe were found out to be very close to each other based on some distance computation. I'll tell you what that is. So that was combined first, and the distance between these two, suppose it was some value 1. Okay, 1. So at that point 1 on the y-axis, I'm really sorry, the screen is not working properly. At that point 1, Lisa and Joe has to be combined, and there is a what do you call it? There is an entity at the dendrogram appearing in between Lisa and Joe there. Okay, then you again look into the different cluster points, and you can see that Alan and Max, not cluster points, data points. You can see that Alan and Max are the next closest data representations. So those two are grouped together, but you can see that it's not at the same level, because the distance between Alan and Max is a bit higher than Lisa and Joe. So maybe it's just imagine it is some 1.4, or okay, 1.4. We'll just take it as 1.4. I think for this example itself it is 1.4. Okay, so at that point we are grouping Alan and Max. Again, this process is repeated. We are going to find out whichever is having the nearest distance. And surprisingly, at the next level, you can see that there is no more grouping between Caro and Nora. What has happened? We are grouping at the next level. Next level is here, right? Here, which all data entities have been grouped? Caro has been grouped with this particular cluster. It's not with individual data point. You're grouping Caro with Alan and Max. So it means that at each iteration, you're computing the distance between the existing data points and the new clusters that are formed, right? It's not with the data points among themselves. After grouping at a particular level, then this itself is considered as a data point. Then you compute the distance between the data points to the existing clusters also. Okay, and here you can see that this cluster and this data point is grouped together at this particular level. Maybe it is some 3 or 3.4, some value. According to the distance between Alan and Max to Caro, this particular grouping has occurred. Again, we are computing the distances. So now we have Lisa, Joe, one group, Alan, Max, and Caro, one group. Then we have Nora. So you have to find out the distance between Lisa, Joe, Alan, Max, Caro, and Nora. Among them, which is having the closest distance. We can see that at the next level, this is being grouped, which means that these three are grouped with Nora at a particular level, some value. Finally, you just have now two clusters, Lisa and Joe and these three, and that is grouped together to form the final hierarchy. Okay, it might feel confusing now because you have not seen the numbers numerical part. I'm just showing it as uh, a surface level view for this entire process. Okay, so agglomerative is when you start with individual data points, you move ahead, group and move ahead and find the final root node or final entire data points together. Divisive is when you start from the parent node and then you divide into different subset based on other distance measures, which we won't be looking into. We'll be looking into the agglomerative part as part of your syllabus coverage. And from agglomerative, we'll be as part of agglomerative, we'll be starting from the individual data points, group it, form the dendrogram. We'll learn how to formulate the dendrogram and how the distance computation is measured. So this is how that dendrogram appears. Okay, so just imagine this is the actual data set: Alan, Lisa, Joe, Max, and Caro, and we have two features on which we have collected the data from these particular people. So it is, we asked people how many hours a week they spend on social media platforms and in the gym. So you can see that Alan spends 2 hours on social media and 3 hours on gym. Lisa spends 5 hours on social media, 2 hours on gym. So we are trying to find out common type of people or people with common characteristics. That's what we're trying to find out, because we don't have a final outcome here, right? We don't have a y variable. We're just trying to group these people into common categories. Okay, so first thing that we can do is, with these values, need not read through this. With these values, what we're trying to do is, same thing has been repeatedly told. So, okay, this is where the process starts. We are taking these values and we are plotting it as a scatter plot. Then you can visualize it more. From the scatter plot, which two values do you think are very close to each other? How did you plot this? You just have the values ranging from 0 to 5 maybe. So you're indicating the value 0 to 5 for social media at the x-axis and for gym at the y-axis 0 to 5. Don't consider it, consider the accuracy part of this numerical representation. This is just for visualization purpose we are taking. Okay. Normally we don't start with the scatter plot and all, we directly compute, but this is just for visually understanding how hierarchical clustering works. We are just plotting this in a two-dimensional representation with social media on the x-axis and the gym value on the y-axis. It can be the other way around also, because both are input attributes itself, x1 and x2. We don't have any outcome variable, so any way you can plot. Then for each of the candidates, Max, Ellen, Caro, Joe, and Lisa, we have plotted it. So which do you think visually are very close to each other? The most minimal distance. Can you just tell me who all are at very close distance? Max and Ellen? Okay. I personally felt Joe and Lisa, maybe because I know the answer, so I might have a tendency to lean towards Joe and Lisa. But anyone else, yeah, I think Joe and Lisa is the ones having the least distance. Okay, so the first grouping has been done. Joe and Lisa is having the least distance, so they are grouped first. Okay, now we don't have. Now, the next thing is most important. After grouping Joe and Lisa, we don't have individual entities Joe and Lisa. We have just this cluster. Okay. This is a hierarchical process. So once you have found out the most close entities and you have grouped it, then in the next iteration, what we consider is this itself is one entity. Then we have Caro, Max, and Ellen. Next, you're going to find out which all entities are the most close to each other in the next iteration. Okay, so in the next iteration, we do have only 4 data points. So which might be the closest one in the next iteration? We don't have individual data points, Joe and Lisa. That needs to be kept in mind. So maybe Max is the first point, Alan is the second point that can be taken, Caro is the third point, and this cluster itself is the fourth point. Understood? So which can be considered as the nearest people in the next iteration? Only 2 can be clubbed. Max Ellen, right? Obviously, Max Ellen is the nearest one when you look into these 4 data points. So Max and Ellen has been grouped in the next iteration. After that, in the next iteration, we do have just one entity as Joe Lisa, another entity as Max Ellen, another entity as Caro. We just have 3 data points. Now we have to find out the distance from Caro to these 2 clusters. Actually, it's not a common distance measure that we take. There is a different distance measure that comes there. We'll see that. But that is the criteria. So you may get confused, which is having the shorter distance. Probably, I feel like Caro is more closer to this cluster visually. Just by applying logic, I just feel Caro may be wrong because I don't remember the final answer. We'll just look into this dendrogram. Yeah, I think Caro, Nora is connected to Nora. Oh, Nora is not there, so that's not the example, right? Okay. Anyway, let's see what we have drawn. Yeah. Here, Caro, I think, can be connected to Joe and Lisa as of now, right? 1 and 2. Vidya ma'am, I didn't get you actually. You're telling that, oh, these 2 clusters are of the same distance. Yeah, maybe that can also happen. So these computations will be done as part of a matrix, and then we'll be doing it in an authoritative way. Right now, we are just visually finding it out. So there might be mistakes. If ma'am has told that these 2 are closer to each other, we'll be grouping this. Then we'll have 2 data points, this particular cluster and Caro. In the next iteration, we'll simply group that because we need not find out which are closer. That is the final step. And if somebody else has an opinion that these are the ones, Caro and Joe and Lisa was the one that was having nearest distance value, that can also be done. But this has to be done based on the computations, not just visually. This is just for understanding the process. Okay. So this is the example. Max initially, Joe and Lisa, Max and Ellen is group. Then Joe, Lisa and Caro is group. They have gone in a different order. But let's see. In each step, the clusters that are closest to each other are always merged. So now what closest together means? Okay, we have 2 kinds of distance measures. As I told earlier, we have point-to-point distance measure that we actually know. We do know that how each points are connected to each other. How do you find the distance? That is Euclidean distance, Manhattan distance. And we also have a method of maximum distance. In maximum distance, it's nothing but whichever is the maximum value, whether maximum value falls in the x-axis or maximum value falls in the y-axis. That is only a difference. That is the case with Euclidean, that is the case with distance between 2 points. But when it comes to distance between Euclidean and Manhattan, we discussed earlier, I'm not repeating it. Maximum distance is when you have the maximum value, when we take the maximum value among these 2 absolute values. Okay. Now we still have to determine how to find out the distance between 2 clusters. We have a cluster here, we have a second cluster here. As we told earlier, we need to find out the distance between these 2 clusters. How do you find out the distance between 2 clusters? That is also very important. So in that case, we have 3 methods. As far as hierarchical clustering algorithm is concerned, we have 3 methods for finding out the distance from one cluster to another cluster. Because we have multiple data points involved, you cannot directly say that, okay, only just one method is that. We have 3 options for that. So when you're given with a question in hierarchical clustering, generally, what kind of distance measure has to be used will be indicated. Point-to-point distance, Euclidean, Manhattan, or maximum has to be taken. That will be indicated. Additionally, cluster-to-cluster distance measure, whether you have to follow single linkage, complete linkage, or average linkage. These points will be given in the question itself. Then only students can answer it, or anyone who is trying to attempt hierarchical clustering can answer it. Okay, so what kind of linkage has to be followed? That also has to be mentioned, because these 3 are equally good. There is nothing like single linkage always gives the best answer. Then we had to learn only that. So at different situations, these 3 interchangeably has provided good results. Okay, so single linkage indicates, it's very easy to understand. Single linkage is when you're trying to focus the most minimum distance between the we are trying to find out the distance between the data points that are minimally distant in these 2 clusters. Is that clear? Single linkage is when you're finding out the distance between the closest entities in these 2 clusters. So here in this example, it's very clear that Caro and Joe is having the closest distance, and the distance between Caro and Joe will be considered as the distance between these 2 clusters, C1 and C2. Okay. When do we need this? you need this distance computation when you are trying to group at higher levels. When you already have clusters as data points, you may have to find out the distance between clusters. At that point, you have to decide what kind of distance measure has to be used for combining the clusters. So when you have to find the distance between clusters, you have to look in the question whether single linkage, complete linkage, or average linkage is given. If it is single linkage, you're going to find out the distance between cluster as the minimum distance, distance between the closest elements in the clusters. Similarly, complete linkage is when the distance computed or distance considered as between the farthest elements in the clusters. Fine. So here it is Joe and Max. You may argue Caro and Lisa is also farther. Maybe it's with computation they have found out that Max and Joe is the farthest. So this is the distance that needs to be considered. Okay, so these are not done visually. These are done by computing the Euclidean distance itself. The distance measure, what is indicated, that has to be done for each of these data points, and then you have to find out the farthest value. So then we'll be using complete linkage. Next case is average linkage. How we have done is using visually just for understanding how it is done, but process is you have to compute it for everything and the maximum value is taken. You have to compute it for every combination, take the minimum value. That is how it is done. Average linkage is when you compute it for everything and the average of all the pairwise distance is computed. That is average linkage. Fine. So for the example that we discussed, we are going to see how to apply a hierarchical algorithm with the help of Euclidean distance and single linkage method. The same can be then later applied to Manhattan distance or maximum distance, average linkage or complete linkage. That is up to you. Just the computation will vary, process and method will be same. Until this, it is somewhat clear. The main concepts in hierarchical algorithm: two different kinds of distance measures, when to use it, why do we use it, what is dendrogram. Until this is clear. Yes. Okay. So we'll move ahead. We'll move ahead with the computation, I think, right? We'll do with the actual example and see how it is working. So we have these two, this example itself has the case study, Max, Ellen, Carol, Joe, and Lisa. Now we need to represent the distances so that we can easily find out which is having the lowest distance or which elements are closer to each other and so on. So we formulate a distance matrix for this. We are going to compute a distance matrix, which comes in handy when you have to compare the values. So as we do with correlation and all, correlation matrix you might have seen, wherein the distance between different one feature to itself and the other features are computed, or even in graph adjacency you might have seen such a matrix. You're computing the distance from one data point to all other data points. This is the quickest or easiest representation that can be used for representing the values. Okay, so we know the values of Alan as 2, 3, Lisa as 5, 2, Joe as 5, 3. We are considering all these as data points. We are considering all these as data points and you are computing the distance. So how do you compute the distance between, obviously Alan and Alan is going to be 0, right? You need not compute it. But how do you compute the distance between Alan and Lisa? Alan and Lisa. You have the point 2, 3, you have the point 5, 2. We are given that we are going to follow Euclidean distance. So you can apply Euclidean distance between these two data points and that value has to be written here, right? If you are given with the condition that the distance measure followed is Manhattan, you will be finding out the absolute distance between 2 and 5. You will be finding out the absolute distance between 3 and 2. That will be summed up and that value will be placed here. Process is same, only the computation of distance will be different if you are given with a different distance measure. So right now we told that we are following the Euclidean measure. So can someone just give me an answer for just one value? Remaining, I'm not repeating it. What will be the value for the distance from Alan to Lisa? computing, just the Euclidean distance, square root of 2 minus 5 whole square. So it's going to be 9 plus 3 minus 2, 1. Did anyone get it as 3.16? I didn't actually try. Earlier it was tried and kept, but just yesterday and all I didn't try. So just confirm if anyone have got the distance from. So here, even though I mentioned it here, the distance of Alan and Lisa to be here, you can indicate it here also because it's the same. So we generally, in this distance matrix, we generally show only one half because the other half is just a repetition. Okay, the distance between Alan and Lisa can be represented here. So then you just go for the upper diagonal part or you can go for the lower diagonal part. That is up to you. So Alan and Lisa distance, I've got it as 3.16 here. Yeah, Jisha ma'am has also, and Sunita ma'am have also told the same. We have got the value as 3.16. So you compute, same thing you repeat. You are going to compute it for all the combinations. Alan and Lisa, Joe and Alan, Max and Alan, Caro and Alan, Caro and Lisa, Max and Lisa, everyone. All the combination Euclidean distance are marked. Why these zeros is something that I need not mention. I think it's just from the point to point, Alan to Alan, Lisa to Lisa, Joe to Joe. That's why that is indicated as 0. Now, what do we have to do? You have got all the distance measures. You are going to look into the minimum value here, right? You're going to find out which are the closest one. That's what our interest was in. So you're going to find out the minimum value in this, and you can see that 1 is the minimum value. Remaining all are higher than that. When you look into 1, the corresponding data elements are Joe and Lisa. From the visual itself, we had already got that Joe and Lisa is the closest among the data points. So Joe and you, from this also you got that Joe and Lisa is the nearest among each other. This is just the computations. Yeah, this is where we found out the minimum value, and Joe and Lisa is now combined to a single data point or single cluster. Now the thing that you have to be careful about is in the next iteration, yeah, Joe and Lisa, now the dendrogram also will be drawing alongside the algorithm at each step, at each iteration. So now Joe and Lisa is combined at the distance value 1. So this dendrogram has to be also plotted at the value 1. So when I share this content, I'll mark the y-axis and give. Actually, y-axis marking is missing here. Here it has to be 1. This particular point is actually 1. Distance is 1. Okay, so in the first iteration, Joe and Lisa is combined and the dendrogram is updated. The clusters are also updated. In the next iteration, what we have to do is, as I told, Lisa and Joe are not separate entities anymore. They are combined to a single cluster. So your new data points are going to be Alan, Lisa, Joe, Max, Caro. Similarly in the column wise also. So you know the distance between Alan and Alan. You know the distance between Max and Alan. You know the distance between Caro and Alan. That was previously computed. That is there. You also know the distance between Caro and Max. That was there. But the distance between Lisa, Joe to Alan, the distance between Lisa, Joe to Max, and the distance between Lisa, Joe to Caro, these three are not known to us. We need to compute that. Right? We need to compute that. So for computing that, we have to find out the distance from these cluster data points to them. We are told that we are following single linkage. So the minimum distance needs to be adopted. Minimum distant point from this cluster to the other data point has to be adopted. So here we can see that from Max and Alan, they are closer to Joe. When you compute it to Lisa, it's going to be higher. You can actually compute it. We have to actually compute it and then put it here, not just visually do it. We have to compute the distance from Max to Joe, Max to Lisa, Alan to Joe, Alan to Lisa, find out which is the lowest value, and that has to be placed here. So accordingly, from here, for easiness, we are directly taking that Max and Alan is closer to Joe, and we are computing the distance from Joe to Alan and Joe to Joe to Alan and Joe to Max. But the advantage is that you need not compute it again and again. All those values are already there in the initial matrix. That is the interesting thing. All the values that we mentioned now, if you want to compute from Joe to Alan or Joe to Max, Alan to Max, all these values are directly takeable from this matrix. You just have to compare it in this matrix, find out which is having the lowest value, and then apply it here, reuse it here. You need not compute it again and again, right? Did you get that point? You need not compute the cluster distance each time with new values or with new computations, because we are following the single linkage method in which we identify which is having the lowest, smallest distance or nearest elements are found out. So if you identify that, for identifying that, you can use the initial distance matrix, find out from Joe and Lisa to Max and Ellen, whichever is having the lesser value from this initial matrix, distance matrix, and then reuse that there. Okay. So from Joe to Max, what is the distance that is indicated in the initial matrix? Joe to Max. Joe to Max, you can use that. You can see that it is 4.12. So in this updated matrix, I'll show you. In the updated matrix from Lisa Joe to Max, which means Joe to Max, that 4.12 is reused. You are not computing it again. Okay. Similarly, from Allen to Joe, the value might be 3 in the initial matrix. Allen to Joe, the value is 3, so that value is reused in this updated distance matrix. Okay, so this is your updated distance matrix. Now, what you are going to do? What should be found out? You are again trying to find out which is having the minimal distance or the closest entities. So here you can see 3, 4.12, 3.16, 2.24, 2.83, and 1.41, of which directly it is visible that 1.41 is the lowest value or the minimal value, which means Max and Ellen is having the next closest distance. You are going to group Max and Ellen next. Max and Ellen is grouped. So in the next iteration, what happens is, again, then and there itself we will be drawing the dendrogram with the value 1.41. Okay, so here it is 1. For the second level, it's going to be 1.41. That is also indicated there. So once Max and Ellen is grouped and Joe and Lisa is grouped, for the next iteration, your data points are going to be Caro, Max, Ellen, Lisa, Joe. These are going to be your data points. You have to fill in this matrix, of which you already know some values. A few values are already there. You need to compute only the new cluster values. Wherever Max, Ellen comes up, from there to Lisa, Joe, you have to find out the distance, and that you can reuse by comparing Max, Ellen, and Lisa, Joe entries in the initial distance matrix, find out whichever is having the closest values, minimal value is taken and replaced here, and the process continues. Now here you can see that 2.83 is that is for the distance computation. Finally, here Lisa, Joe, and Caro. Lisa, Joe, and Caro has the least distance 2.24. Caro and Lisa, Joe. So this Lisa, Joe, and Caro will be combined in the next iteration that is done here. Dendrogram is also updated accordingly, which is not shown, but dendrogram has to be updated based on this representation. Lisa, Joe, and Caro here. This combination has been tried out. Then you already had Max, Ellen. You only have to combine these two directly. We don't have to compute any more distances. We combine these two, and what is the distance between these two clusters, that will be represented in the dendrogram here. Okay, and the final group of data points after the agglomerative clustering is formed. This is how hierarchical clustering is performed, and if you require, according to your requirement of how many clusters you require, you plot this dendrogram at that particular level and you form the clusters. That is what ideally we do for hierarchical clustering. This is clear. Maybe I'll take a quick 1 or 2 minutes and I'll just review this once again, because it's a long process. Even though the computations are very simple, only the first distance matrix has to be computed. From that itself, you'll get all the values at every iteration. You need not worry about it at all. But when you explain it, it's quite a lengthier task. I'll just start over once again. Quickly go through the process. So for hierarchical clustering, two things that has to be kept in mind is you have to understand how the distance between 2 points is computed. It can either be Euclidean distance, Manhattan distance, or it can be maximum distance. You also have this problem of computing the distance between clusters, because iteratively at each iteration you might form new clusters. So the number of data points will change accordingly. The new clusters will be taken into account as the data points. So you need to find out how the distance between clusters are also computed. For that, we have 3 popular methods. One is single linkage, complete linkage, and average linkage. Single linkage is when you compute the distance or take the distance between the data points that are very close to each other in the opposite clusters. And complete linkage is when you take the maximum distance between these two clusters, data points in these two clusters. And average linkage is when you consider the average of all the distances between these clusters. These values are taken from the initial distance matrix that we compute. Then in the example that we have taken, I've told that we are using the Euclidean distance and single linkage method, in which we first compute the distance matrix based on the Euclidean distance method and update the distance matrix. And I told that we just have to focus on either the lower diagonal elements or upper diagonal elements because it's just a repetition. From the distance matrices, distance values computed in that matrix, you'll be finding out the minimum value. Here the minimum value was the first iteration was 1, and that was corresponding to Lisa and Joe. So Lisa and Joe was combined and the dendrogram was updated. In the next iteration, that particular cluster has to be considered as a data point and the other data points remains the same. Again, you have to find out the new distance values from that cluster to the data points. For that, you can refer the initial distance metric. You have to follow the single linkage method here. So you have to find out, is it from Lisa or is it from Joe that Alan is having the shortest distance? So that can be referred from the initial distance matrix, whichever is having the lowest value that is taken here, and it is updated. From the updated distance matrix, again, you are finding out which is the lowest value. It was for 1.41, that was for Max and Ellen. Max and Ellen is grouped, dendrogram is updated. Then for the next iteration, 2 clusters comes up. 1 data point, Caro is also there. Again, there are some missing elements, missing entries for which you look into the first distance metric and update those entries. Repeat this until all the elements are combined together into a single whole cluster, and you draw the dendrogram. So dendrogram is also a very important result of the hierarchical clustering part, because the distance values and the hierarchy at which where you can split this clusters, that is available only from the dendrogram. It's not the visual representation, 2D representation that is required. Dendrogram is the most important concept in hierarchical clustering. Okay, so if you are given with such a question, perform hierarchical clustering for the following data points using Manhattan distance and complete linkage. What will be the difference that you will have to sort out? I'm not detailing it now, but you can attempt it, but I'm just asking you how to start off. How to calculate the distance between Lisa, Joe, and Alan Max. Lisa, Joe, and Alan Max, again, I'll just tell you once again. I think you didn't get that concept. Okay, let's erase this. So many might be having the same doubt. So for computing the distance between Lisa, Joe, and Alan Max, as I told, we have to find out which are the elements that are closest to each other. Okay, Lisa, Joe, and Alan Max. So we will be referring the initial distance matrix. Here you can see that Lisa to Joe distance is 3. I've taken the eraser part once. Lisa to Joe distance is 3. Then what all were the matrices? I mean, groups Lisa, Joe, and Alan Max, right? So you have to find out the distance between Joe and Max, Alan and Lisa, Max and Lisa, and Alan and Joe. All these combinations have to be found out, and whichever is having the minimum value, that has to be considered. So Max and Joe, right now we saw for Alan and Joe. Alan and Joe, we got it as 3. Then we have to find out the distance between Alan and Lisa. You can get it from here, 3.16. Okay, then we look for what we took now, Alan and Lisa. Alan and Joe is over, Alan and Lisa is over. Then Max and Lisa, Max and Joe. Max and Lisa, 4.47. Max and Joe, 4.12. So which do you think is the minimum value? Because we are following single linkage criteria. Minimum value is 1. No, not that one. We are talking about the distance between these 2 clusters. Okay. Then, we are focusing on these 2 clusters. So finding out the distance between these 2 clusters is based on the single linkage criteria, which means that we are identifying the data points which are closest to each other in these two data points in these two clusters, and we are finding out the minimum value. Don't look at this highlighted value. This is for the previous purpose, the initial grouping we had marked it. Right now, I'm just telling you how to find out the distance between these two clusters. So for performing single linkage, you have to find out the distance between all the combinations and find out the minimal value. So you have to find out the distance between Alan and Lisa, Alan and Joe, Max and Lisa, Max and Joe. So those four combinations have been highlighted here: 3.16, 3, 4.47, and 4.12. Lisa and Alan is 3.16, Joe and Alan is 3, Max and Lisa is 4.47, Max and Joe is 4.12. Among this, which one is having the lowest value? It's showing that I lost my network connection. Probably the screen is not visible, or are you? I mean, am I audible there?
Everything is fine, ma'am.
The screen is also
Screen,
displayed.
screen sound, everything is fine.
Okay, okay. Here, my screen is showing that I've lost my network connection. I'll just wait for a second. 1 second. I'll just connect it to my. Also, can you see the updates there? I have circled the distances: 3.163, 4.47, and 4.12. Is that visible?
Yes, ma'am, it's visible.
Until that, it is visible. Fine.
Yeah, clear.
If at all my sound goes up, just let me know, because it's constantly showing that it is.
But at this end, it's fine. Now it has been.
I think it got disconnected now. I was keeping on telling, but when I came back and looked into the chat, by that time it got disconnected. Uh, am I
Yeah.
audible? I'll share it once.
Right now, you are audible, ma'am.
Okay, okay. In between, I think it was breaking.
Yeah, it got broken.
Is the screen visible?
Yes. Now it's visible,
Sorry,
ma'am.
I didn't actually happen to know what happened, but then it got lost. Network
It's
connection.
okay, ma'am.
Okay.
It's okay.
So we were telling. 1 second. I hope you heard till
Yes, that 4 points were highlighted and the shortest distance
distance.
was.
Yeah, the distance between all these combinations were found out from this distance metric, and we found out that 3 is the lowest value or the smallest value, which means that Joe and Ellen is having the closest distance. So if you want to find out the distance between these two clusters, Max Ellen and Joe Lisa, you will have to take this smallest value 3. So when you represent it in the metrics here, Joe Ellen and once again Joe Lisa and Max Ellen, the distance between these two here, it will be replaced with 3. Let me take the pen. It has to be replaced with 3. I'm not sure if there is any computation issue. See, Lisa Joe and Max Ellen, you can see that the value replaced is 3. Is that clear now? How we ended up with the value 3? I forgot who asked. I think the remaining previous chats will not be available. Jishan, was it you who asked how to compute the distance between Lisa Joe and Max Ellen? Okay, okay. Sorry, I didn't notice. I mean, note who asked, because I got disconnected in between. Fine. So I hope you have understood how to replace that value with the value 3. You can just refer to the previous distance metrics. Everything is there. All values are there. You just have to have a perform a comparison there and replace the value with the new metrics. I mean, replace the value in the new metrics. Okay. So for every combination, you have to do this. So this we did it for since it is single linkage. Now let me ask you, if I am using the same metrics here, just for computing the distance between Lisa Joe and Max Ellen itself, I have these many sets of values, right? If I'm following complete linkage, can you tell me what value has to be replaced there? if I'm following complete linkage. Good, 4.47, correct. And if I'm following average linkage, you will have to find out the average of these 4 values. That will be the value that we use for replacing in the new matrix. Is that clear? Yes. So only when the distance between clusters computation comes up, it's a bit different concept. You have to use a linkage criteria. So we have to know what linkage criteria is whenever you handle with hierarchical clustering, not just the distance measure. Okay, so we were talking about the next question, although we won't be for solving it, but I just want to ensure what all changes you will be trying out. If you get a question like this, hierarchical clustering for the following data points using Manhattan distance and complete linkage, what has to be done? How do you start? Ma'am, is the session till 12:30 or 12:45?
12:30, ma'am. 12:30.
Okay, so with this example, we'll stop for the session. Afternoon, we'll start with neural networks.
Okay. Okay, sure. Thank you.
What all differences do you apply? Initially, the first difference is that we are using the Manhattan distance. So when compared to the previous example, when you found out the distance metrics, the first distance metrics between Joe, Lisa, and Max and all, there we have to apply Manhattan distance. Instead of Euclidean distance, you are going to compute the Manhattan distance. Then once the distance metrics are computed, you try to find out the closest points among the Manhattan distances computed. You form the first set of cluster. In the next iteration, you'll be having one data point lessened, and you'll have reduced number of data points, right? One will be cluster and the other will be data points. Then you can refer to the initial distance metrics computed, find out the linkage criteria. Linkage criteria here is complete linkage. So as opposed to the previous example where we focused on the minimum value, here we'll be focusing on the maximum value, find out the maximum values, replace the or update the new distance metrics with the maximum values instead of the minimum value. And complete the iteration, you'll be getting the update the dendrogram then and there, and then find out the answer. If you want the solution, if you want to try it out, you can try it out. But these are the only difference that you have to update. So you can give questions as combination of Euclidean distance, Manhattan distance, maximum distance, and with different linkage criteria: complete linkage, average linkage, and single linkage. So this itself is maybe a 15 marks question. Like if you give all combinations, and you can compare the different results that you get, and which distance measure will be better for a particular data set can be found out. So I think I better not start neural networks now because it's already 12:25. If 12:30 is the break time, then is it okay if I stop now?
Yeah,
or-
we'll wind up this session right now, ma'am. It's okay.
Okay.
Ma'am, so this session was such an explanatory and it was so clear. Hope everybody could follow it. So thank you so much for the session. So we'll wind up for now. Then the participants be back by 1:30 after lunch break. So we'll resume the session by 1:30, ma'am.
Okay. Thank you, ma'am, and thank you for the warm feedback. Thank you.
Thank you so much. Okay. Thank you to all the participants. So please remember and be back by 1:25 itself so that we could start the session by 1:30. Thank you all. Have a great time.
Ma'am, is it okay if I leave the session? It's so fine, no? I can join at that time.
Yes, ma'am. Yes, ma'am. You may leave, then rejoin by 1:25, ma'am.
Fine, thank you.
Thank you, ma'am.